Hello students, welcome all you to the IMS GATE Academy. Myself Ravi Bogdula. Today in this session, we will see the quick revision on operating system. The first of all, I would like to start why the quick revision is important. So exam is very near. So GATE 2023 exam is near, that is next the February 4th, right? So before this examination, the revision is very important. So what is the benefit of the revising this subject? So if you revise the subject many times, so during the examination, the questions are jumbled. Questions are it is not in order of the subject. So any question can be come, in any order. So switching becomes, easy, like contest switch becomes very easy. The revision is very important prior to the examination, so that during the examination, the shifting from one question to other question becomes very easy. So today together we'll revise the entire operating system, spending some 2 to 3 hours. So the revision means you understand here. So most of you already prepared the short note for each and every subject that consists of hardly 10 pages, right? So you understand those 10 pages we are going to be revised in this session. So which contains, so what are the things we are going to look into this revision session? You understand the very important topics, important statements, so necessary formulas to revise and remember for the exam point of view. And these are the things we are going to be observed during our session. So together we'll start the session for revising from the beginning to end of the subject. So let's begin the subject. So first, so before starting any topic, let me give it the what are the topics are there, what are the topics from the operating system and weightage. So how many marks, how many questions we can expect from this subject, that we'll observe first, then we can start the actual topics now. The syllabus, operating system syllabus already but let me write it. And before starting this session, I would like to say everyone, so this is this session specially for dedicated for the GATE 2023 aspirant. So those who have already prepared well and so you are under revision mode, So साथ में together we'll revise this entire subject, so that you will not confusion during examination, in a examination hall. So you are not in a position of any confusion, understanding what the topic is talking, what is this question is talking about. So that is a major motto of taking this session. So let me write the syllabus. What are the syllabus? What are the topics, major topics from the operating system? So in terms of chapters, if I divide it like operating system, the first chapter I can write introduction. So introduction to operating system, the chapter 1 you can understand. Here you might be studying what is mean by operating system, various components of the computer system, various components of the computer system, various components of operating system, and followed by types of the operating system, classification of operating system, see. So what is mean by what is the differentiation between the uniprogramming, multiprogramming? Good evening, Jagdish. Very good evening. So you might have learned difference between what is the uniprogramming, multiprogramming, multitasking, a multi-user, a distributed real-time operating system. So this distinction already So that kind of things you already studied. And the followed by, please understand, from the introduction part, so you need to revise this system call concept, system calls. So system calls are very essential topic for GATE examination is considered, because so many papers if you observe, previous year papers if you observe, so we could see the question from the system calls. The system call, the special cases you understand, the fork system call is there, the fork system call. Questions have been framed on this topic several times, and this question is easily solvable also, So let me take the one. So I would like to take one example for this also. So we'll see. So let me first of all write the so the topic which we need to be understand. So the first chapter is concerned majorly, you can focus like, because this introduction part, like what is operating system, what are the components, this may not be answered, then may not be like frame the question. But from this topic I could say like, system calls are very essential. From the introduction part, the system calls are very essential. And so in that case also the folk system call, if we can expect the question. So what kind of question we can get? So most of you already practice. Let's take the sample also. What kind of question we can get from system calls? Let's see. And second chapter concerned, that is chapter 2. Chapter 2, process management. From process management. So what are the important area? What are the topics we need to be revised? So what are the topics which you already written under your short note? So like, the process, what is mean by process? Yes, somebody could answer. What is mean by process? The process is nothing but a program under execution, right? Other way you understand, when the program you taken from secondary memory and loaded into main memory for execution, associate some various resources, that become a process, right? The loaded, please understand, whenever programs comes into main memory for execution, that becomes a process, because which includes the various resources. That is active entity, dispatchable, schedulable unit, right? The basic unit of CPU utilization is a process. The process you understand already. So process, you have seen the process, various process states you studied, various process states like new, ready, running, the block or wait or termination, suspend. There is various, the process state, you understand, process state indicates or depicts the activity of a process during its execution time or during life cycle of the process. It is changes the various states. And go and focus the process state transition diagram. Reason, we can expect one question also. We can expect, so theoretical question we can expect from the process state transition diagram. From 2000, like now if you see the past 2-3 years onwards, if you see the MSQ questions, multiple select question type, right? We have the type of category. And the computer science is a branch where we can expect the more MSQ questions that happened. If you go and see the previous year paper, like 2022, 2021 paper, so we could see the more than 10 questions from the from CSC, like where we could see that MSQ questions. And among all, you understand, operating system is subject where we can expect the more questions, more MSQ questions. Like what is the area, sir? Process management is the area. I can say like process state transition. Like they can give us some set of statement. They can ask which of the following is true or which of the following is false. So you have to be very clearly the understanding the various states, what is meant by ready, running, and ready to running to block state, block to ready state, ready to suspension, ready to termination. We have, right? This is a transition well prepared, so that whatever type of question being framed, so you are in a position to answer it. So we will see that the process states also will observe. So process, what is the process? Process state, the transition diagram. The followed by very essential thing is what? The CPU scheduling algorithm. CPU scheduling also known to be process scheduling. The various scheduling algorithms are there. We'll look at, we will see. So then followed by please understand, most important topic, IPC, inter-process communication synchronization. IPC, inter-process communication synchronization. Here, so definitely please understand, we can expect the question like 2 marks question. It can be 2 marks question. It can be 2 mark question. We can expect 2 marks, sometime 1 plus 2, sometime 2 plus 2. Happened previous papers. If you see, best example I can say 2013 paper. From this topic only, IPC synchronization topic, there were I think 6 marks, 5 to 6 marks were there. So 5 to 6 months, almost 4 or 5 questions have been framed from IPC synchronization only. That important. And the most of the people have a lot of confusion under IPC synchronization also. Let's have a little discussion over this topic, because one should not leave a topic from the operating system, so, that is what IPC synchronization. You must go through, like you have to read this subject, you have to read this topic. The followed by we'll see like deadlock. So another important topic from the process management what deadlock. So these are the various like subtopics from the process management you need to focus. The CPU scheduling algorithm, so we can answer like accuracy is high. Naturally we can get the numerical type question from CPU scheduling algorithm, and IPC synchronization we can get the objective type question or MSQ question can be framed, and deadlock also possible 1 to 2 questions. Fine. So these are the topics need to be understand from process management. So let me write the third chapter is a memory management. Memory management. Memory management. You understand, all of you, the beauty of the operating system one can able to understand while learning this memory management. Memory management is a very key important topic, key topic from the operating system. Like the practical, if you see the running of the larger program into smaller memory, that can be understand very well. So after studying memory management, like virtual memory concept is there. The beautiful topic and a very interesting topic also you have studied, and that is the reason I am telling this is a topic where we can expect again 1 or 2 questions, like 1 question or 2 question can be framed from the memory management. Various memory management techniques are there, so that will observe here. So here, so one should focus the basics of the basics. So basics of the memory management, that is nothing but visualization of the memory, how we can visualize the what RAM, like RAM or main memory, you understand. The various memory management techniques includes contiguous allocation, non-contiguous allocation, The followed by we can see the virtual memory. This is very important, where also we can expect the questions. So in this area we can expect the questions like this. So these are the topics you need to revise from the memory management. The final is like a fourth one is file system. From file system we can expect the question like you need to revise is the file allocation methods. Followed by disk scheduling. And the physical structure of the disk, anyway you studied from the computer organization point of view, like physical structure, like you understand there are 2 types of questions we can expect from the physical structure of the disk. Like one is time based, one is space based. They can ask question what is the size of the disk. Sometimes they ask how much time required to read a sector or some file size from the disk. So this kind of question we can expect from that area. And the pure operating system is concerned, we can see file allocation methods, various file allocation methods, free space management, and the disk scheduling algorithms are the major important topic from this area where we can expect the question. Fine. So fine, these are the 4 units I am classifying. So introduction part, process management, memory management, file system. Yes. So when we'll move to the first chapter, the introduction part, one should focus on the system call, that is 4. So let us look at the system calls, all of you. So let us look at the system call. Chapter 1. So chapter 1. So that's introduction part. Introduction to operating system. Here. So I hope most of you are aware of this various types of operating system. So what is meant by uniprogramming, multiprogramming, right? So I hope you know already what are the essential hardware support is required in order to design the multi-programmed operating system. That is essentially required address translation, DMA support, at least 2 modes of CPU operation. So when you have a 2 modes of CPU operation, whenever all user program, user application will run user mode, and the privileged instruction, that is operating system programs, will run a kernel mode. Whenever user program required a service from the operating system, so this user program make a request to the operating system via system call to get the service from the OS. The system call, there are various system calls out there. So process control system call, memory management system call, device related system calls, file related system calls, right? So communication related, information maintenance related system calls are there. So one of the system call I want to take up, that is the fork system call, fork system call. Is basically it is available in Unix operating system, equivalently create system call in Windows operating system. Create system call is what? In Windows operating system. Fork is available Unix or Linux operating system, understand. So you know essence of the system fork system call, right? It will create a new process. The creation of the new process happens, you understand, exactly duplicate of the original process, exactly duplicate of the original process, that you know already. Let's take suppose example, if I take, so main, if I take the program, suppose example fork followed by suppose printf. Here printf I am writing hello, understand. If I run this program, the program contain the fork, this will create the new process, please understand, new process. This we call new process, or we can call the child process. What is this child process contains? The child process contains as it is duplicate of the original fork, duplicate of the original process. Fine. Okay. Now, if the program child to be continued for execution, child has to continue the next line of the current fork only, because you understand the child process created because of this line, the fork, right? Fork part of the process, this called, then because of this fork only this got created, you understand. Child has to start the next line of the current fork, you understand, next line of the current fork. And parent also start, anyway this line is over, it has start from here. This one important point you need to understand. If the children to be continued, it will complete, it will print hello, this also will print hello. So total new process will two process will be there, number of new process would be 1, like this. So now similarly like suppose, like if I take fork, so fork, so like this, you know, suppose if you have n forks in a series, n fork in a series, like question we can expect how many new processes, how many new processes can be created, how many new processes can be created. So this type of a question we can expect. So very simple, this observation comes to while taking the samples, like no, you run 1 fork in a series, or 2 forks in a series, 3 forks in a series, that we can extend it into n forks. If the forks are in series, please understand, forks are in a series, then number of new process will create equal to 2 power of n minus 1. This understand. So 2 power n will be the total number of processes including parents, total number of processes, and new process would be how many? 2 power of n minus 1, where n is the number of forks which are kept in series. This will work out for the only number of forks in a series form. This understand. So various questions framed, like example. So there was a question like int I, like getting my point, main the for I is repeating 1 to 10, understand, I is repeating 1 to 10, then if so this I divided by divided equal to 0, this suppose modulo giving 0, now they run the fork here, fork they run, getting my point is now. So this is only program, understand. For this, so they asked this question, very recent paper, 2018 or 19 paper perhaps. So they ask how many new process can create, yes, you understand. I is repeating how many times? 1 to 10. Whenever I is divided by 2, like this given, I modulo 2 equal to 0, 0. What values of I? This will be condition is true. What values? So I equal to 2, 4, 6, 8, 10. 1 to 10 I repeated. 1, 2, 3, 4, 5 times repeating. 5 times, please understand. 5 times this condition is true, means 5 times the fork will run. 5 times means you understand, one fork is repeating 5 times or 5 forks will be kept in a series. Same, right? So the number of new process would be 2 power of 5 minus 1. That is what? 31. As this gate question, this is a gate question. Like that we can expect the question. And another type of a question also we can expect. Another type of question means to understand, like another variation I can give it. Main function is the main function is given like please understand, if fork or fork. Getting my point? Printf. Hello. I hope you understand. Now here a question, what kind of question it is? So they ask how many new process will create. One type of question we can expect. Or how many yellows are printed. Another type of question we can expect. Sir, how to check, sir, this one? Very simple. This is very essential point here. This question also can be modified into, in place of OR operator, you can place logical AND operator. So all of you should notice about the meaning of the logical OR operator and logical AND operator. Let's take A, B here, A, B, take it like this. These two are operands. Based on the meaning of this logical operators only, and the evolution of the fork will happen. So what you have to notice, all of you, A or B is there. So this operand, left side operand is a positive value, positive, so non-zero, please remember, positive value, then it won't check for the right value. It won't check for the right operand, so total condition going to be true based on the trueness of the left side operand. That is the meaning. If the left side operand is 0, then it will check for the right side operand. Means you understand, if this return value of the fork is positive, it won't evaluate here. If you are not evaluating this one, nothing, another child will not create it. That's the meaning you understand. When there is a condition is true, this get created. So that you understand. OR operator says that if left side operand is a positive, the right operand is not evaluated. When it comes to AND operator, if left side operand is a 0, please understand, it is not positive value, 0, then it won't check for the right one. Means if the left side operand, converse of the statement, if the left side operand is a positive, it will check for the right one. AND operators, and both should be correct. Both should be correct. Means if it is positive, it will also should be checked. If it is positive, then total condition is true. If it is also not like 0, then total condition going to be failed. Nothing but if condition going to be failed. That you have to understand. So in this property, then you can evaluate, you can get the answer for this question. So possible question from this code, what? They can ask question, how many new children created, or total number of process executed, or how many hellos are printed. This possible questions you can expect from this area. Got it, all of you? So now go and little practice and revise this concept. That's it. That's enough from the chapter 1. So quickly move on to the chapter 2, that is process management. So second one is process management. Process management. Wherever it is necessary to spend the time, we will understand all of you. As I mentioned, from the process management is concerned, the major 4 topics will be there. First is the process concepts, right? So process concepts. The second one is the CP scheduling or process scheduling. The third one is the IPC and synchronization or concurrency also understand, concurrency. The fourth one is a deadlock. All are important. All 4 topics are important from this one. You should not leave any topic. So nobody should leave the this or the topic. One more important point I would like to share all of you. Operating system, the solving the accuracy will be more. If you know the concepts properly, and accuracy will be more to get the marks, you understand. Because see, when it is considered about the process concepts, the statement wise questions will get naturally. If you are good at the concept, and picking that statement will becomes easy. When it comes to CPU scheduling algorithm, I'll show you what type of question we can expect and what are the major algorithm repeatedly asked in the previous papers. In that few terms will be there, those terms only repeatedly asked. But when it comes to IPC synchronization, there will be synchronization mechanisms. They can give directly mechanism, modified version, modified synchronized mechanism, or some new type of code given some property they'll ask it. So deadlock, there are 2-3 types of question we can expect from the deadlock. We'll see one positively. So look at the process concepts. Look at the process concepts, all of you. Process concepts. So process concepts means, I hope you know the meaning of the process, as I mentioned earlier also. Meaning of the process, how we can understand of the process, right? And when it comes to process states. As I mentioned, process state defines the activity of a process during its execution. So there is a process state, new, ready, running state, running, yes. Another thing is what? Another thing, the block state, block or IO state, and termination, terminate. Or extra 1, 2, 3, 4, 5 state, I am adding a ready suspend state, ready suspend, and block suspend state, These are the extra state we can say. So total 7 state model. New, ready, running, block, terminate, ready suspend, and block suspend. These are the various states we can understand. And process transitions also need to understand. Process transition means the process changes state during its execution. It changes states during its execution. Let's have a quickly revision on this process states. Okay. So let us look into the process states, various process states. As I mentioned, we have a state called new, where a process being created, right? Process being created, understand. The various data structure for a process being created, like allocation, creation of the PCB. Creation of a PCB happens by the operating system. Once a process is created, this moving into main memory, where the state is called what? Ready state, we call. After this creation, after created, then process move eventually to the what ready state, that is in main memory. So another state I am showing, that running state, nothing but you understand. Execution state, this is CPU. We do the dispatching, nothing but precision. What is the meaning of dispatch? So take a PCB of a process from main memory, the ready state, and submit to the running state, you understand. During process execution, if it is required any service from the operating system, like it is issuing any event is issued, or maybe require the IO operation. So process eventually has to come from the IO state and do the IO activity. Then you have to send back to where ready state, you understand. Once execution is over, please understand. So once completion of the process, move to terminate state. Terminate means, you understand what is the meaning of termination? Halting of a program, end of a program. Termination, nothing but resource deallocation takes place here. So another state I would like to add, what I said, ready suspend state, So ready suspend state. Another state we have a block suspend state, So processes we suspend from where? So block state, yes, suspend. So this, based on the requirement, we can resume it here. Suspend from ready state here, suspend from ready state, and based on the availability, we can resume the process here. So these are the various state transition, and I would like to show that what. So this is what a preemptive based operating system. Running process forcefully deallocated from CPU to and sent back to memory. Based on understand there are two situations. If the operating system willing to take the additional process which is having high priority over the execution one, so you have to preempt it. Or under time sharing system, the process which is using the CPU might be reached the like maximum allowable to use the CPU, then the running process need to be preempted here. Now, so what is the purpose of ready suspend state? What is the ready suspend state? Please understand. So whenever operating system willing to take the high like some more processes into system and there is no memory space, now some of the ready process we suspend into secondary memory. You understand? Ready suspend state is state which is in secondary memory. You understand? Secondary memory. If I say process in ready suspend state, nothing but that is in a secondary memory. Operating system temporarily swap out a process from main memory to secondary memory to accommodate the space to new arrival process. The new arrival process might be the high priority. Getting my point? So this we do the suspension here, and based on the availability of the memory in main memory, then process can be swapped in from disk to main memory. That will happen. This activity done by, please understand, this activity done by the medium term scheduler here. Now processes load, please understand, processes loaded from secondary memory to main memory done by the long term scheduler, we know, and the dispatching will happen by the short term scheduler. There are three types of scheduler you might have studied: long term scheduler, medium term scheduler, and short term scheduler. And once any process, please understand, any process who came for IO activity or event to satisfied, once this activity is over, IO or event is over. So this eventually has to move from the block state to unblock state is a ready state. This is also done by the medium term scheduler. So what is this transition, sir? Block to block suspension state. You understand, normally operating system choose a process for suspension under a various reason is a ready state. Ready state is a desirable state. Please understand, all of you please note of it also. There could be statement is a question. Which of the following is the state, which of the following the desirable state to select for suspension? That is a ready. Normally operating system choose a ready state for suspension, but sometimes we choose a blocked process also suspension. Reason you understand, the process who is doing IO activity having the least priority over all the processes in the system. In this moment memory is already full, operating system willing to take additional process. Now obviously operating system has to choose one of the blocked process for suspension. You understand? Another way you understand, another situation also you understand, operating system is taking additional process that require more memory and one of the blocked process holding the large memory size. Now operating system willing to, so will do the suspension of the blocked process for into secondary memory. This also secondary memory. This also secondary memory only. So like this various transition, there's a few important transition I shown you all of you. So this is the 7-state model. From this we can expect the theoretical question like MSQ question can be expected. Like what kind of things, sir? Suppose if I ask you what are the transition possible or what are the transition not possible. So let me put up like in terms of one. So ready to please understand, ready to running state, running. So like just I'm putting question, what are the possible transition, what are the not possible transition? There are two type of question, ready to running. So I'm putting running to terminate. Running to terminate, possible or not you can tell. Running to termination, running to ready suspend, fourth one. Running to ready, fifth one. Running to block, sixth one. Running to new state, seventh one. Block state to running state, eighth one. Block state to terminate, terminate. Ninth one, block to ready state, block to block suspend state, block to block suspend state. 11th one, block suspend to ready suspend state, ready suspend. I would like to show this transition we have. Okay, so whenever this IO or event is over, event satisfied, so this process will move to ready suspend state here. And 12th one, ready to terminate. So suppose these are the possible states. Some states I mentioned, transition mentioned. What are the possible? Ready to running, yes, under dispatch this is possible. Running to termination, yes, halting. Running to ready suspend, yes, this we can do, please understand. So this transition also possible, understand. This transition also possible. I hope you understand. From running to we can suspend. What the circumstances are? Please understand. Already memory is full. Now operating system so take up additional process, wanted to take the additional process having high priority. Now process which is running in a CPU state having the lower priority over the system, pura complete system में this running process having the lower priority. Then operating system has to choose running process for suspension. So this is possible. Running to ready under preemption possible. Running to block state when a required IO activity. Running to new state not possible here. New state is where process being creation, right? So already done. So block to running, this is not possible. Block to running, please understand, under multi-programmed operating system, the moment process goes for IO activity, another process being scheduled. Now somebody already using the CPU state. Now the process who's completed IO activity cannot go to running state. It has to go to block state only. So ready state only. So block to termination possible. Reason, suppose some process using the IO activity block state, suppose it given some illegal issue, like you understand, illegal request to the what particular device, which is not true. So now process can be terminated. From any state process can be terminated. That abnormal termination we call. Normal termination after completion after execution of the process will be normal termination. Abnormal termination can happen from any state. Otherwise you understand, process in a running state, so process in a ready state and children process in IO state, and the process is terminated in ready state. Now forcefully all children process need to be terminated. You know, right? Parent process if it terminated, if it is terminated, all children process has to forcefully terminate it. Wherever this children process would be, they has to be terminated. That you would understand. Now block to termination happen. So block to ready, yes, this is the finest thing. This is done by the medium term scheduler. You understand, whenever a process like usage of the IO activity or it is might be waiting for an event which is occurred, so eventually process has to move to the ready state only. So we have block to ready possible state. The block to block suspendence, I given a transition because whenever I said you naturally operating system choose a process from the ready state for suspension, but some circumstances operating system forcefully choose a blocked process for suspension. This state also possible. So block suspension to ready suspension, yes. So the process which is in a block suspend, which is waiting for an IO. Once this event or IO satisfied, eventually that process will move to ready suspension state where it will sit saying that I don't need any IO activity, all done, I'm just waiting for execute as soon as you load from secondary memory to main memory. So this transition possible. Ready to termination, yes, possible. As I mentioned, a process can be terminated from sitting into any state, that you have to understand. So these are the some possible states are, some not possible states are there. You note of it all of you, because The two type of question we can expect. Which of the following states are possible? Which of the following transitions are possible? That's MSQ question. Or another type, which of the following transitions are not possible? Also a MSQ question. You can get it, ma'am. Fine. Sometime you understand, sometime all of you. One more question I would like to put. What transition indicates the operating system is a multi-programmed preemptive based algorithm, preemptive based operating system. What transition, like which state of the transition indicates or denotes the preemptive based multi-program operating system. So you understand, all of you, the transition which you have in the running state to running state to ready state. Running state to ready state indicate this transition. Preemption, presence of ready state indicates what multi-program operating system. So very good evening, sir. Gopal sir, very good evening. So I hope you understand. These are the areas you can get it. And one more important thing you need to notice. So short-term scheduler, medium-term scheduler, and what? Long-term scheduler. There are three types of schedulers we have. The presence of the schedulers also I said you. So now these schedulers will help us to know scheduling. Scheduling, you understand. The CPU scheduling nothing but what? Short-term scheduler only. So you understand CPU scheduling is nothing but the implementation part happens what? Short-term scheduler only. So now let's move on to the next topic. What? CPU scheduling algorithm. So let's move on to the CPU scheduling. So let me add the pages. So CPU scheduling. The purpose of the CPU scheduling, most of you already aware of it, right? Purpose. Why we need to apply the CPU scheduling? Very simple thing to understand. We want to implement the short-term scheduler. So implementation of short-term scheduler done by understand dispatcher. What is the dispatcher? It will pick a process from the memory, that is main memory, ready queue, and assign to the CPU, right? When this ready queue having more than one PCB, now selection decision is need to be made for selecting a process from ready state. So some kind of decision policies need to be implemented, so need to be used for selecting a process. So there are various decision making policies. To understand these various decision making policies, some kind of criteria, some kind of metrics need to be kept. Those things you already studied. So understanding like CPU, maximizing the CPU utilization, right? CPU utilization, maximize the CPU utilization. Utilization nothing but usage of the CPU, and maximize the so maximize the throughput. So throughput of a system. And third one is the minimize the first one, turnaround time. Second one, waiting time of a process, and third one, the response time of a process. So these are the metrics, various metrics. So these are the various metrics. You understand, various metrics are various objectives of the CPU scheduler which were imposing on the various decision making policies, so that we can select the optimal scheduling algorithm for implementation, because these are the requirement to meet. So various scheduling algorithm when you introduce, we have to check the performance of the various scheduling algorithm. Whichever meet these all the things, then you can be chosen for implementation. Yes, Rohit, very good evening. So I hope you are appearing for GATE 2023, and this is a session, it is going to be help you a lot, like stay connected. So let's together we can revise the things from the operating system. As I mentioned earlier also, like this session specially for dedicated for the those who are studying, appearing for the GATE 2023 only. Already those who are already studied, this kind of revision only we are doing. It is your short note, we are going to do it like that simply. Fine. So these are the things need to be understand. Throughput, right? What is the meaning of throughput? Somebody, because question they can frame, find the throughput of a something system. What is the throughput? Yeah, somebody give answer. What is the throughput? Yes. Throughput means throughput nothing but number of processes or jobs are completed per unit of time. number of process complete per unit of time. Unit of time could be a second or milliseconds, or you can put it in terms of hour also. This within 1 hour, how many process completed by the system, that is throughput. The turnaround time, nothing but the submission time of a process to its completion. This interval, time interval between the submission and completion indicates the turnaround time. And waiting time, you know, right? Process naturally wait for a CPU allocation, a ready queue, that waiting time. So waiting time need to be minimized. Sometime process may also wait for the acquiral of the IO devices, or it wait for the event to come occur, right? Then, so response time, nothing but the time at which first request we submitted to the system, its response start generated like this. So I am just putting a request, and when it is start generating the response to us indicates what response time. So this all the things to be minimize it. So now along with this, the various process times you need to understand. You have to very clear about the what is meaning of arrival time, what is the meaning of completion time, what is the meaning of turnaround time, as I mentioned already. Then waiting time of a process, and so other things like the arrival time, the time at which process is enter into ready queue, and another thing was schedule time. So these are the various process times you need to understand. Arrival time, the time at which process loaded into ready state. The time at which completed the execution is the completion time. Turnaround time is the total. Waiting time of process would be the waiting time waiting for a the CPU allocation, right? Schedule time, the time at which process is scheduled for execution. Otherwise, the time at which process start contacting into CPU. So that way you can understand. Suppose a particular process PI is there, okay, I loaded into ready queue at time that we call arrival time. Now it will be in a ready queue, right? It will be in a ready queue for some time. Let's take it as waiting time 1 and writing like this. After some time it will get a CPU for execution. So now bus time of a process BT1. So bus time nothing but, and let me write here also another thing. So we need to notice the next thing was bus time. So bus time or service time of a process. This two could be two things. One is CPU bus time, and second was IO bus time. CPU bus time or IO bus time. Now see, look all of you. It is spending in a CPU, that's CPU bus time. After that, suppose it required for IO, it wait for the IO. Let me take the waiting time as a 2. Then after that, it got IO completed. Then came back to ready queue. So waiting time 3. Then after some time, it got a CPU. Then execute the bus time of a 2. Assume that. Suppose some preemption occur, it will again come back to ready queue, right? So waiting time 4. Then it will get a CPU. Then bus time, let's take bus time 3. So then it's completed. Assume that. This is a completion time. This completely time interval will be there. This we call it turnaround time. So turnaround time. So now how I can define turnaround time of a process would be completion time minus arrival time of a process. So this parameter is very important. Many times or several times we have seen in a previous year papers, question asked like what is average turnaround time? What is the average turnaround time? So another thing is waiting time. We can find out how to get the waiting times. So this waiting times you capture, how to get this waiting time. So total bus time if you remove from the turnaround time minus bus time. Turnaround time minus bus time gives a waiting time of a process. So I hope you understand finding the turnaround time, finding the waiting time. Question obviously they ask, what is the turnaround time? What is average turnaround time? What is average waiting time of a process? This will ask. So we'll look into the various scheduling algorithms. So let me give a list. Then we'll see the possible questions. Let's see the possible questions which we can expect from the CPU scheduling algorithm. The first algorithm you study the first come first serve, right? First come first serve. The followed by shortage of first. Yes or no? The followed by shortest to remaining time first scheduling algorithm. Followed by longest to remaining time first algorithm. followed by highest response ratio next, followed by priority based CPU scheduling algorithm, the followed by round robin algorithm, followed by multi-level queue scheduling algorithm, followed by multi-level feedback queue scheduling algorithm. So these are the possible, the various scheduling algorithm you might be studied. Fine, I hope you. And from this algorithm, majority time, please, I could see the questions here. This is, I can put it many stars like this, understand. So these are the areas, and one time they asked like this. I am putting many star for this, like this, understand. Many years papers, I seen a question from shortage of first and shortest remaining time first algorithm, and round robin is a common scheduling algorithm. I could see various papers, and sometimes priority based scheduling algorithm. Let's have a quick revision on this, and please understand what is our motto. Please, I mentioned these are the requirements. Various scheduling algorithm, they ask to meet, these are the requirement. We call scheduling criteria or scheduling objectives, and which are the algorithms are satisfying the things here. So look at the first come first serve. In this case, please understand, I'm writing here. I will write it. I will write the points. Better I will write it. Here. So whether it is, I'll write it, whether it is preemptive, so whether it is non-preemptive, I'm taking, then so better let me properly write it, because this will give the good information. So anyway, you noted, right? So you noted the list of the what scheduling algorithm. Let me write scheduling algorithms. Fine. The first one is the first come first serve. Second one is the shortest job first. Third one is the shortest remaining time first algorithm. And fourth one is what? Longest remaining time first scheduling algorithm. Fifth one is a highest response ratio next. Sixth one is a priority based scheduling algorithm. Seventh one, let me restrict with the round robin only, till round robin. There are, that is, other two are combination of these algorithms only. Then I am taking the points here. So what are the algorithms comes under non-preemptive, because this can ask question in terms statement wise. And what are the algorithm comes under preemptive. And what are the algorithms suffer from starvation problem is there, starvation. And I'm taking average waiting time, average turnaround time, and what are the things are minimal. So I'm taking what is a minimal, I'm taking minimal, average waiting time, average turnaround time. So let us look at these points here. Okay. Now first come first serve comes under non-preemptive algorithm. Please understand, non-preemptive. First come first comes under non-preemptive algorithm. Getting? And starvation, it is not starvated, please understand. And not minimal, we won't get minimal average waiting time, minimal turnaround time. Reason, first come first serve, what happens, which we observed. If the first two process is a big process, all has to wait for that one. So that will increase the average turnaround time, average waiting time. Otherwise, it is a simple algorithm, I can say. And shortest job first is what? It is a non-preemptive algorithm, basic nature. And it is a non-preemptive. Starvation, yes, starvation is there. Why? Longer jobs are starvated. And here minimal average waiting time, minimal turnaround time, response time will be not minimal. So this will get it. Shortest remaining time first is the, so I'm making cross mark. This is shortest remaining is not a non-preemptive, is a preemptive. And here also starvation will be there, and a minimal average waiting time, minimal turnaround time will be there, but more contest switches, please understand. Shortest remaining time first algorithm generate the more contest switches than the shortest job first, you understand. And sometime you understand, like most of the shortest remaining time generate the minimal average turnaround time comparison to the shortest job first. That you have to observe. So longest remaining time first, it is not a non-preemptive, it is a preemptive, it is also preemptive. And here also starvation would be there. Starvation for shorter jobs. Longest remaining time first algorithm, in this case what happens, shorter jobs are get starvated. Here it will be what? So we can expect longest remaining time first also. Sorry, like here you understand this also we can get it minimal. Minimal compared to first come first serve, like this. Compared to first come first serve, this will get a minimal average waiting time, average turn, because sorry, what happens here, they will spend longer job, they will spend the longer job, they will spend the more time in a process, more time in a CPU, means understand more interaction would be there in case of longest. You understand, it is opposite, simply opposite to the shortest remaining time first. Highest response ratio, it is non-preemptive, it is a it is a non-preemptive algorithm. So non-preemptive, it is not a preemptive. Please, highest response ratio, it is what algorithm do. It is also favor to the shorter job, but also limit the waiting time of a longer job, you understand. So there won't be starvation here. There won't be starvation. There won't be starvation. Now average, minimal average waiting time, minimal turnaround time under highest response ratio would be, so it will be minimal comparison to, please, comparison to first come first serve. Comparison to first come first serve. Like, it is like a shortest job first, but one more point I am making, minimal I am getting nothing, but it is not that much minimal compared to shortest job first. Priority based CPU scheduling, it can be preemptive, it can be non-preemptive, please understand. Priority based CPU scheduling algorithm can be preemptive, non-preemptive. One more thing I would like to say, here I am marking minimum average waiting time, minimum average turnaround time, nothing but it is comparison to I am taking the short first come first serve. But if I compare with the shortage of first, it is not that much minimal also. Now see, priority based CPU scheduling algorithm can be non-preemptive, preemptive. Starvation would be there here. Starvation would be there if I choose the priority as a static priority if I use, so starvation problem will be there. So it can be minimal, it cannot be minimal here. Round robin, it is not non-preemptive, it is a preemptive based, please. Round robin preemptive, and here please understand, round robin case which are not minimal, so no starvation at all. Here it is a more responsive. Round robin, please understand, generate the more responsive. Responsiveness is there, means response time is less. Under round robin algorithm, response time is less. But average waiting time, average turnaround time, if I observe, that is not minimal, which will take more. So no starvation will be there. Starvation won't be there. So these are the observations we can do it now. I think this table is good enough for comparison the various scheduling algorithm. So that's all. So quickly one example I can take for you. Look this. Which of the following statements are true about round robin CPU scheduling algorithm, they are asking. Okay, statement 1, that option 1. Read the option 1. Number of contest switches in round robin increases if the Q time quantum, TQ time quantum 1 and number of process n. Means saying that, which you learn already, performance of the round robin scheduling algorithm completely depends on the time quantum value only. If the time quantum is less, more contest switches would be there. See now, number of contest switches in round robin increases, time quantum value is 1. The statement 1 is true. Second statement, number of contest switches in round robin decreases if the time quantum value equal to 1. So number of process n, this is false. response time in round robin increases. This is false. Response time in round robin decreases. Please understand. Response time in round robin algorithm decreases, means process is more responsive. So like every process is not required to wait for long period of time to get at least some response from the process. It will get immediately, because every process share the CPU with equal time interval, like we have a time quantum, right? Next, if the time quantum equal to maximum burst time, then the round robin degrades first come first algorithm. Is true. Please understand. If the larger time quantum value degrade that algorithm into first come first serve, that you should observe. Getting my point? As we studied, right? Round robin is algorithm is what? It is a preemptive version of first come first serve. Preemptive version of first come first serve with what is a property? Time interval. So time quantum or time slab value chosen. Getting all of you? Yes, this way we can answer it. This way we can answer it. So one more question. Yes, this is all about this enough. This is enough from the what? This process management. CPU scheduling. The third one will see IPC part. IPC and synchronization. IPC and synchronization. IPC synchronization, concurrency. Concurrency. This is the third aspect from the process management. What are the two aspects? First one, process various concepts, then followed by CPU scheduling algorithm. For that, I drawn a table. I think that information is sufficient to understand. And what are the questions? As I mentioned, what are the questions we can expect? What are the questions we can expect from this one? As I mentioned, most of the time they asked, what is average turnaround time? What is average waiting time? What is the completion time of a process? What is the throughput of a system? What is the schedule length? What is the efficiency of the processor? Or sometimes you understand, all of you see, along with the CPU burst, you also try to consider the IO burst and try to draw the Gantt chart. They can ask sometime question, at what time particular process completed its IO activity, or how much percentage CPU setting ideal during this schedule. This kind of possible question they can make it. Are you getting my point? If you take any scheduling algorithm, you draw the Gantt chart, right? During this particular schedule, how much percentage is the CPU setting ideal? So just count it, the context to the CPU, just count the weight, divided by our schedule length, you will get the value. And carefully you do it, question they mix with CPU burst time as well as IO burst time. You run CPU as well parallel IO. Parallel IO would be there. Parallel IO nothing but each process having its own device. So they can run parallelly. They have to draw the Gantt chart. They'll ask some completion or average waiting time or content, that's percentage CPU idealness. This kind of question we can expect. That's happened previous papers. Fine. So I hope you understand from the process CPU scheduling algorithm what are the things to be revise or understand. So quickly move on to the IPC synchronization and concurrency part. It is very important topic, and most of the people feel little difficulty in this. But what I'm trying to say, if you go like from scratch level, beginning level to understand the various topic clearly, then analyzing the code becomes easy. Here is like you have to trace the code. Tracing of a code is very essential. If you are able to trace properly, then answering the questions from this area becomes easy. So sir, what is IPC stocking? Very simple to understand. In a same machine or a different machine, when are two independent process, they want to communicate each other. Communication happens in two ways, which I know, right? Communication happens two ways. One is message passing system. Second one is shared memory. Second one is shared memory. Shared memory nothing but suppose there is a memory segment, virtual memory is there, it is shared by multiple process, or there is a file required to be shared by more than one process. And message passing system, which is established by the connection established by the operating system by providing some kind of operating system we call primitives or resources, like we have pipes, message queues, which are acting like transmission medias, and which are established in the communication between the two processes A and B, and one is send, other is can be received. So there are two ways the process can be communicated. So now you understand, you might have studied this all the things, and what is our focus need to be go here. We are not going to deal with this, how this is communication is established and what are the mechanism to establish. The point you understand, during their communication, are they synchronize each other? Are they synchronize each other means what? What kind of problems we can get it during this inter-process communication. So you might be noticed, so that some many times it is leading to inconsistency, data inconsistency means when two or more processes are trying to access some shared data, during this execution time, some kind of different results comes, so that you will notice. And occurrence of this problem, and to solve that problem, various mechanisms need to be understand. So we have to implement it, like, so best of it I can say semaphores are the best synchronization primitive synchronized resource which used to solve the all IPC problems, critical section problem basically we say, right? So if I ask you question, lack of synchronization lead to data inconsistency, so loss of data I can say, and it is perhaps can lead to deadlock state, right? Deadlock state. Now to address this problem, what are the various mechanisms are there? Other way understand, what are the necessary conditions for occurrence of the critical data inconsistency or synchronization problem. Somebody could give it, what are the essential condition which causes the synchronization problem. The first one is we call critical section, or we can call critical region also. Second is what is the race condition. Race condition means multiple processes are racing to access this shared data simultaneously. And occurrence of the preemption. Occurrence of the preemption. If all three conditions occur simultaneously, so there is a problem of what? Data inconsistency. Am I right or wrong? If all three conditions occur simultaneously, there is a problem of data inconsistency. That's what we call synchronization problem, for which we need to look the solutions, right? One of the paper 1 mark question they have framed like, what is the meaning of critical section? The statement is like that. So I am telling you, all of you, critical section is a part of the portion of the program code, you understand. Program code is some portion of the program code where shared resources access that code. Shared resource nothing but multiple process trying, they can access this code, the particular code. We call critical section, critical region. The best example you have studied from, one classical IPC problem, that is what? Producer consumer problem. In a producer consumer problem, there is a variable called count. Producer want to increment and consumer want to decrement. Both are sharing the common variable what? Count. Correct? So during this share, this inconsistency can be created. That part we called as a critical section. So not only presence of the critical section, like race condition is nothing but more than one process trying to access the shared code simultaneously. Then the final results of that shared resource can be expected, the process which finishes the last, right? Suppose sometime question asks what is the minimum number of process can be allowed to guarantee guarantee the race condition. So other you can avoid the race condition, how many process, minimum process need to be allowed for critical section 1. If I not allow more than one to race, then there won't be a problem. So preemption is allowed, a preemption as we studied. Under multi-program operating system, the preemption is there, means user process can preempt any movement or n number of times during their execution naturally. And when it comes to kernel code, privileged instructions cannot be preempted. So during their execution, they will execute atomically, atomic nature they execute. But our user programs are bound to preempt any movement of the time and n number of times. So this you have observed already, right? So these are the we can understand the essential or necessary and sufficient condition to say the problem of what synchronization problems. To solve this one, so we need to develop the various synchronization mechanism. And to develop the synchronization mechanism, as I mentioned, under CPU scheduling algorithm, if we want to develop any CPU scheduling algorithm, we must have some kind of criteria, some kind of metrics need to be imposed on various algorithm to get the optimal algorithm. Similarly, we have to impose some kind of conditions or requirement, we can say, and to pick one good algorithm for synchronization. So necessary conditions, sorry, requirements for the synchronization mechanism, I can say requirements. So requirements for synchronization mechanisms. What are the requirements? The first requirements, what? Mutual exclusion, please understand. See, race condition which we observed means more than one process racing to access the critical part, then problem arise. We have to ensure that where there is a shared code is there, at least only at a time only one process is allowed to use that critical section. Getting my point? No two processes should interfere in this critical section to access. That will create a problem. That's what we have to ensure the mutual exclusion. Not only inclusion, mutual exclusion and progress condition also need to ensure. And third one is a bounded weight. And by considering the architectural neutral, no assumption and the no architectural like speed or slower. So I'm making the architectural neutral because bounded weight nothing but uses of the no process should ever wait for access the critical section forever. Getting my point? No process has to wait forever to access the critical section. There must be bound to access, there must be bound the limit on the waiting time to get the critical section to use it. What is the meaning of progression? Yeah, what is the meaning of progression? When the critical section is free, please understand, what is our objective? We have to ensure the mutual exclusion to access the critical section. Means allow only one process to use a critical section at a time. That means you understand, if the critical section is free, anybody can try, but only one process need to be allowed, right? Progression says, please understand, whenever critical section is free, anybody can try, only one process is allowed, right? That we know. But what progression is saying that when this critical section is free, no process should stop. So no process should stop other process who are willing to enter into critical section whenever the critical section is free. Means some process who is running outside the critical section should not stop the other process who is willing to enter the critical section when the critical section is free. This kind of situation should not happen. So that need to be ensured. I hope you understand. These are the essential, like this is a primary requirement, I can say. This is a secondary requirement, I can say bounded weight. The primary requirement what? So guaranteeing in the mutual exclusion as well as the progression condition. So let us look into the various synchronization mechanism. What are they? What are those? Like what are the algorithm which satisfies these are the conditions? Like what kind of questions we can expect from the gate point of view, that we'll observe. Fine. So look into. Let me write the first. Various synchronization mechanisms. Various synchronization mechanisms are first one. The first one, please understand. I'm writing like first one is so like lock variable. Second was strict alternation. And third one is the Peterson solution, also known to be Decker's algorithm. Peterson solution also known to be Decker's algorithm. So next one is the TSL instruction. TSL means, what is the meaning of TSL? Test set lock. The fifth one is so like disable interrupts. Sixth one is a semaphore. Please understand semaphore. The semaphore also comes under one is counting semaphore. Second is a binary semaphore. One is counting semaphore, otherwise what? Binary semaphore. So when it is comes to, please understand, when it is comes to like what are the condition it to satisfy? Mutual exclusion and progression, right? Progress. progression. Please understand. So if you look at these algorithms, all of you, if you look at this algorithm, what are the things, what are the algorithms are satisfying? Lock variable you have studied, right? So what you need to understand, all of you. So I don't want to discuss the code, detailed code of the various these algorithms. Let us see the performances. What are the algorithms are like satisfying our requirement? Then what type of question we can expect that you understand. Look, I am strongly recommending all of you, if you are not revised well, go and revise all algorithm. Why? What is the benefit you will get? Many times I have seen exactly code, whatever the code you learn from this various algorithm given as it is, they will ask some parameter asking whether it satisfies mutual exclusion or progression or leading to deadlock or both of them, or other type of question they can ask by giving data, or sometimes they will fill in the blank, they will ask what should be there in this line. Many times even like under lock variable, strict tolerance, Peterson solution, TSL instruction, like this. Fine, go and observe. So when it comes to mutual exclusion, lock variable, mutual exclusion is not guaranteed. Yes, it will fail to guarantee. So if it is not guaranteed, nothing, progression will be there. So mutual exclusion not guaranteed, nothing, it is allowing more than one process. Allowing more than one process, nothing but nobody is stopping when critical section is free. So that is satisfied. But this is not suitable to implementation. I am making mark, not suitable to implement. Reason? The primary requirement of any synchronization mechanism to what? Guarantee the mutual exclusion is not satisfying. When you see the strict alternation, you know, right, mutual exclusion guaranteed, but progression is not guaranteed. This also not chosen for, and it is limited to two process solution. Now when it comes to Peterson solution, it is satisfying what? Satisfying the mutual exclusion progression also. And what is it? It is restricted to only two process here. TSL instruction satisfies the mutual exclusion progression, and it is more than two process. Now understand, earlier operating system they implemented the TSL instruction. TSL instruction has implementation. Then it disable interrupts, this can satisfy, but is not choose for user level application. Reason? Disable interrupt, simple statement says, before enter into critical section, disable all interrupts and just enter the critical section. Use before leaving, then enable them. So during execution, no interruption will occur. So interruption no occur means there is no presence of the what problem at all. This will satisfy all the things, but not choose for what is not chosen for user level application. Now semaphore will satisfy all the things. This is implemented, this practical implementable. Semaphore is a practical implementable algorithms. Semaphore is a practical implementable. And semaphore, when we study for semaphore, having the major two operation, right? Wait and signal up and down, right? And one thing you need to understand, semaphore operation should be some order. If you change order, that may lead to another problem called what? Deadlock. Usage of the semaphores, if it is not happened properly, then lead to another problem called deadlock. So that you need to understand, all of you. Fine. So I don't want to discuss more. Let us move to directly little discussion on little semaphore. So these are the code. Try to revise yourself, which you already have a code, right? And because advantage would be same code can be asked, because happened many times, or little modification of that, or you understand synonym of the code also given, like you have changing some variable names and all, but ultimately the semantic of the code will be same only. They will ask question, which of the following solution will, like which of the following is satisfies above solution, like satisfy the progression, satisfy the progression mutual exclusion, and leading to deadlock, like this are kind of option they can give it. So this again question, MSQ question can possible, MCQ question can be possible in this area. Got it, all of you? Yes. Chalo, quickly we will move on to the semaphore. So basically, if I talk about semaphore is operating system resource. First thing. Another aspect, if I want to say, semaphore is a variable of itself, semaphore type. What is the data type? Semaphore type. It is a variable of itself, same type. That should understand. So it is taking the integral values. Please understand. It takes what? Complete integral values. Based on this integral values, it is divided two types. One is counting semaphore, yes, and second one is the binary semaphore. Yes or no? Binary semaphore. Both uses, please understand. Let me write like this. Counting and binary, right? And counting, you understand, it takes the values from plus infinity to like minus to plus infinity. It takes only 0 comma 1, please understand. So both are having this two operations called, one is a down operation, down, and second is up operation. Down also known to be P operation, also known to be weight, we know, right? Weight operation. Up also known to be V or signal. So you know meaning of the down or weight P, that is indication decrement one value of semaphore, and this will you have to increment one value of semaphore. This only differentiation would be there, right? Yes. So I hope you already studied the implementation of the down and up operation, but let us look into the usage of this operation, usage of these operations now. Got it? So like you might have seen also the classical IPC problems known to be, there was a question like exactly not remember whether gate paper or other paper, they asked which of the following problems considered to be classical IPC problems. Classical IPC problems. First one, producer and consumer problem. The second one, you understand, reader writer problem. Third one, dynamic philosopher problem. Dining philosopher problem. Sometimes they ask under dining philosopher problem also they ask solution. For a dining philosopher problem, there are two types of solution will be there. What is two types of solution? One is semaphore based solution. We can use semaphore. Another is non-semaphore based solution, like without applying any semaphore, we can also give some solution. Like the philosophers sitting around the table and their natural functionality, what eat, they has to eat when they become, they has to think for the problem. The moment they become hunger, they has to eat it. So life cycle will be goes on thinking about a problem and become hunger, eat it. This is life cycle. If everybody become hunger, then there will be limited force will be there that may causing the deadlock. To break it, the deadlock, there are two solutions: semaphore based, non-semaphore. If it is non-semaphore, there was a question, one more question asked, which of the following solution for dining philosopher problem, they given a statement. If it is a non-semaphore based, one user has to pick left to right forks, and remaining n-1 user has to pick opposite, right to left, they has to pick it. There will be a concurrency, there is some process allowed to eat it. One source. Second solution, even number of process, philosophers can pick it the fork from left to right. Odd number of process, they can start pick the fork from right to left. This also one solution. So this give the some process can start eat, some process nothing, philosophers they can start eat. Like that will be there. Let us first we'll focus on this semaphore now. So look all of you, semaphore operation based some question we can get it. Let's take, if I take the binary semaphore for a t value, t I'm initializing 1, and another binary semaphore I'm taking yes. So yes, I'm taking as a 1. Okay. Suppose there is a critical section, is there critical section, please understand, and there are two processes are there. Let's take process A is there and process B is there, please understand. Process A, process B is there. All of you please observe, Suppose I'm using P of A is an operation followed by P of B, and process B also using like sorry, let me, this is processes, right? P of T, P of S. Okay, getting my point. So P of T and P of S is there, and both are trying to access critical section. Once critical section is over, they can work up V of S, V of T, but the little revision. So V of S, V of T, like this understand, all of you. V of S, V of T, fine. So this is there. Now question, the question would be this code, like this code, the accessing these two process trying to access the critical section will guarantee the mutual exclusion. First statement will guarantee mutual exclusion. Second statement will guarantee the progression and will guarantee the bounded weight. And the statement 4, will it lead to deadlock state? These are the type of question statement they give, they'll ask it. Getting my point, all of you? So what are the statements I mentioned? The statement I mentioned, so I'll write it here only better. So one is guaranteed, the mutual exclusion is guaranteed. Second option is what? Progression. And third one is what? Bounded weight. The fourth one is, will it lead to deadlock? These are the four options are there. So let us answer them. So let us know, this is statement 1, instruction 1, let's say, like instruction 2, instruction 3, instruction 4, assume that. This also same, instruction 1, instruction 2, instruction 3, instruction 4. Getting my point? So let me take under concurrence environment, and ready queue has two process. What are those? Process A comma process B is there. At time t0, the scheduling happen like this. Process A, suppose process A is schedule. Assume that. This is an essential part, tracing part. If you are able to do proper tracing, answering this question becomes easy. So now this is simple problem, but so why you taken simple problem? Some other good problem you could have taken. You can think. My intention to not to solve a problem, to give an idea to trace out, to understand how to test the mutual exclusion, how to test the progression, how to test the bounded weight. So these are the things we need to notice, all of you. So let us look the first process. At time 0, process P is scheduled and eventually start running the instruction 1. What is instruction 1? This down on T, P of T, nothing but down on T. Let me write here T variables, T equal to 1, comma S equal to 1. Down on T, nothing but 1 down 0. You know, all of you, right? There would be two things need to be noticed from the operations on the semaphore variable. One is up and down operations are there. Successful and unsuccessful operation need to be understood. Successful nothing but after perform the down operation on semaphore variable, it becomes still 0, like 1 down 0 is positive. Then we call successful. 1 down something, if we get negative, that indicates the unsuccessful operation. Since 1 down 0 successful, because binary semaphore 1 down 0, 0 down 0 only. Successful means, so statement 1 can run, then it will run to statement 2, instruction 2. What is instruction 2? Down on S, what is S? S value is 1 down 0 success. That means both over it enter into critical section. So to check the mutual exclusion, all of you please understand, to check the mutual exclusion, try to allow one process inside the critical section, allow enter the critical section. Yes, so process P1 in critical section. So critical section nothing but having the instructions only. During this execution, suppose preemption occurred, like apply preemption. I am holding critical section, applying the preemption. If I apply preemption in time T4, process PB might be scheduled. You understand? Leftover process BB only, right? Now you understand here carefully. Process A holding the critical section code and came out of from the CPU, right? Now it is in a second main memory, that is in ready queue. Now we schedule the process B also willing to access same critical section. Whether it is allowed to use the critical section or not, let us see. Eventually it will run the instruction 1. What is instruction 1? Down on T. What is T value? T value is 0. 0 down 0 only, please understand. Since it is a binary semaphore, if the initial value of binary semaphore is 0, after perform the down operation also it will be 0. We call unsuccessful operation. Unsuccessful operation we need to put into Q. That is, you studied, right? Q is a data structure it will use. S dot L is there. L. So I have to block it. I am blocking process A. I am blocked. Assume that process A blocked. It is blocked. Please understand. Blocked. It is blocked. So you understand? Now it is ensuring the mutual exclusion or not. Tell me. Ensuring the mutual exclusion or not? Yes, it is ensuring the mutual exclusion. How, sir? So means that's what, once I allowed one process to inside a critical section, I am trying to allow another process, it is not able to enter because we are ensuring the mutual exclusion. So got it right? Ensuring the mutual exclusion. Now we need to think for the progression. Progression nothing but if the critical section is free, process is allowed to use the critical section or not, we have to observe it. If the critical section is free, whether process, any one process is allowed to use or not, that we need to observe. Let's continue this one. It is blocked. At time T8, please understand. So process A comes, leftover CS part over completed. then completed, this is completed, then we will run the third instruction, fourth instruction. What does mean third and wake up? So yes, V means up operation, T means up operation, T, yes, T becomes 1, S becomes 1. So process B also waked up. So waked up, nothing but it will come to where it is blocked. After first instruction it blocked, right? Then after suppose at time 2 T12 process B comes, it start from where? It got blocked during performing the first operation, right? Yes or no? First operation PR T. So successful, like unsuccessful term, like it went to block state. Now it will check for what? It will check for what? It will check for this only, right? I have to perform this next operation. This operation is over. So this operation over. Process PB during first instruction down on T. T value 0, 0 down, 0 down 0. We blocked it. Then we have woke up. So we woke up, right? We woke up, nothing more, you understand, it will end, it will run the second statement. So second statement, what is second statement? Down on S. What is S value? S value is 1. 1 down 0 successfully, it will enter in a critical section. So now it is in a critical section. It is in a critical section. So now process B in a critical section. In this moment, if process A tries, what happens? T equal to 1 down 0 successful, but S value what happens? 0 equal to 0 down 0 block. So process A going to block. So we are successful in ensuring the mutual exclusion. It is also guaranteed the what progression. How, sir? How it is progression is guaranteed? That's what initially I tried with process A, process B. One of them is entering critical section or not. Nobody stopped. So that means it satisfies what? Satisfy the what? Satisfy the progression also. Progression also satisfied. Bounded weight also will satisfy. Reason, sir? If the blocked process, if the queue is maintained in FIFO order, please understand. FIFO order we call, if the queue blocked process we are keeping in a queue, right? If the queue is maintained with the FIFO order, bounded weight also guaranteed. Suppose if say question, the queue is implemented by LIFO, last in first out, then there won't be guaranteed the word bounded weight, because last in first out, if you see first process going to be weight starvation, right? If the queue is implemented by FIFO data structure, we call queue data, we call strong semaphore. There was a question theoretically, what does mean strong and weak semaphore? Weak semaphore means if the queue is implemented by LIFO order, last in first out, the stack, then we call what? Weak semaphore. If it is implemented by queue data structure, we call strong semaphore. That the difference would be there. Fine. Now we have to check for the deadlock, whether deadlock is possible or not. So let's take the case number 2. Case number 2. Getting my point. Case number 2. Okay. At time 0, please let me start again. Process A started. Instruction 1. What instruction 1? So let me take the T value. T equal to 1, S equal to 1. Sir, how to check the deadlock, sir? Whether the process will lead to deadlock or not. What you do in this code, in the code, execute each instruction, apply the preemption. After every instruction, apply the preemption, then we will be able to know whether it is leading to deadlock or not. Let us see. So process PA started. So statement 1, down on T value becomes 1 down 0 successful. It goes to instruction 2, 1 down 0. So sorry, what you can do, what I said you run one instruction, apply the preemption, right? You run one instruction, apply the preemption. Okay, preemption. At time 2, process B comes, will run the first instruction. What is this is still 1 only. What is the first instruction? Down on T. What is T value? 0. 0 down 0, block. So this will be blocked. Right? Now leftover process is what? If I schedule at time T4, process A only. Process A already run the first instruction over, right? It will run second instruction. What is second instruction? Process A. Down on S. S value is 1, down 0 successful. It will enter into critical section. So one process is allowed. Process A is allowed to use a critical section. Nothing but no deadlock. Please understand. It will not lead to deadlock. This not lead to deadlock. So now if it is MSQ question, which of the following statements are true? Nothing but 1, 2, 3 are true only. If the question says that which of the following statement is false, option D is going to be answer for this question. Like that you can trace it. Getting my point, all of you? Another thing of this, variation of the code, if you see this code only, variation of this code if you observe. Let's suppose, please observe, all of you, please observe. Okay. If this two statement, if I interchange interchange this code, like getting my point, all of you. If I interchange it, let me here. So what I'll do, I write this one code again. So what is the code I'm trying to say? Process A code, right? Okay. Binary semaphore T equal to S equal to 1. Look this, all of you. What I said you, P of T followed by P of S, then accessing the critical section. Then process B is there. P of S interchanging and P of T is there. Getting my point? Like this. So instruction 1, instruction 2, instruction 3 is V of S, instruction 4 is V of T. Third statement is V of T. Fourth statement is V of S. Assume that V of S is there. Getting all of you? Now suppose I am asking, this code is given. So simply I will ask it whether this code will lead to deadlock or not. I will check. So now I am taking, so ready queue having two process A comma process B. Let's schedule, so at time 0, suppose process A schedule, process A schedule. Instruction 1. What is instruction 1? Let me take S equal to 1 comma T equal to 1. Let me write here. S equal to 1 comma T equal to 1, right? Look this, all of you. So P of T means T down 0, successful. Sub apply preemption. Getting my point, all of you. At time T2, if process B schedule, right? Preemption occur. If done the first instruction. What is first instruction? Down on S. What is S value? 1. 1 down, 0 successful. Let's apply the preemption here. Then after some time T4, so process B schedule, both are in, process A schedule, both are in main memory only. A, it will run second instruction. What is second instruction? Down on S. What is S value? S is 0. 0 down, 0 only. It is blocked. So this is blocked. Please understand. At time T6, process B comes. Process B. What is process B? Second statement. What is second instruction? Down on T. What is T value? T is 0. 0 down, 0 only. It is also blocked. Please understand. So it is also blocked. So this leads to what? Deadlock. Please understand. Both are blocked. Nobody enter into critical section. Blocked nothing but, what is the meaning of block here? They went to secondary memory. Blocked indications sending into secondary memory. Temporarily we send the process in secondary memory. Nobody able to wake up it. It leads to deadlock. Sir, what happened here? Please observe here. TS is there. Opposite I used. What? Opposite I used, right? Opposite I used like ST is there. TS and ST is there. That's what I said now. One point I mentioned. Semaphore used to solve the synchronization problem. If you are not able to use the order of these operations, that will lead to another problem called deadlock. I hope you understand. So based on these various questions, many questions I have seen in the paper. Best example I could say, 2013 paper, there was a question. He said concurrently there are 3 process accessing some common code. They are updating some data. And these operations, please notice, these process operations are enclosed by semaphore operations. What order of semaphore operation need to be placed so that deadlock, it will not lead to deadlock question they ask. So means in this case, suppose what order I have to place it to access the critical section, these 2 process, which should not lead to deadlock. T of S, they will give a blank, suppose L1, L2, line 1, line 2, line 3, line 4. They give option. What order we have to place this semaphore operation? This this will not lead to deadlock. So what you have to place it? I said now this should be same P of T, nothing but this also should be P of T. This also P of S should be the same order should be there. Then only it will not lead to, otherwise it will lead to deadlock. That way you understand. I hope you got the point, all of you. I hope you got the point. Let's move on to one example. I have taken a binary semaphore mutex equal to 1. binary semaphore, mutex equal to 1 year, 1. Let n equal to 5 processes, 5 processes, 5 processes where pi is a process, process pi. So each process pi try running what? Want to use a critical section here. So critical section enclosed by operation P of mutex, V of mutex is there like this question. Now this question, if I ask you whether mutual exclusion guaranteed, second one progression is guaranteed, third one bounded weight is guaranteed, and the fourth question, will it lead to deadlock? I am asking here. So verify and tell me, all of you. Just think, you can pause the video and think yourself. There are 5 processes concurrently trying to access some critical section which is included by what? Mutex initialized to 1, P of mutex and V of mutex, while operation are given, continuously they are testing here. Then whether it is guaranteed the mutual exclusion or not. So what I said, you to check the mutual exclusion, all of you, try to allow one process inside the critical section. Then put in critical section, apply the preemption. Let's run. Suppose how many processes are the ready queue containing? Ready queue contain how many? Process P1, process P2, process P3, process P4, process P5 are there. Process P5 are there. Tell me, all of you. Process P5 are there. Now at time 0, suppose time 0, process P1 schedule. So start, right? So this while checking, here is the first instruction. What is first instruction? Down on mutex. What is mutex? 1 down, 0 success. Then directly it will enter in critical section or a critical section. So during this execution, some preemption occurred. Then another process we can schedule, process P2. It will also run first instruction. What is first instruction? Down on mutex. Mutex value what? 0. 0 down, 0 only. Now S dot L is a queue. Getting my S dot L is a queue. I am putting like this. So you have to block it. What you have to block? Process P2 is blocked. It is blocked or not? Blocked. Let's see process P3. What happens? It will also run the first instruction. What happened? This will also run this one. Down on 0, 0 only. So this process P3 also blocked, right? So this is also blocked. Am I right or not? Blocked. So what about process P4? Process P4 also going to be blocked or not? 0 down, 0 only. So process P5 also blocked. Means process P4. So process P5. Understand? All these 4 process blocked or not blocked? Only one in the critical section. That means you understand. So mutual exclusion guaranteed or not? Guaranteed. What about progression? Progression also. How, sir? If nobody is there critical section, one process can entered. So what about bounded weight? Bounded weight also guaranteed. Since the Q I maintain the FIFO, I am writing FIFO. If the FIFO means Q data structure, if I use it for unblocking, so P2, P3, P4. If I use LIFO, last in P5 you have to unblock, then P4, then P3, P2, then there is a starvation. If I use it LIFO to store the blocked process, you understand the bounded weighting is not guaranteed. That is going to be starvation. If it is implemented by FIFO, guaranteed. What about deadlock? So deadlock. So we applied preemption deadlock. There won't be problem with deadlock here. So deadlock will not happen. Suppose all of you, instead of P operation, if I put it V operation, then what happens? Here suppose, what I am trying to say, if P operations are replaced by V operation, V of mutex is there, then tell me how many process would be in a critical section? Every process? Am I right or wrong? V operation, see, first process comes to perform V of mutex, 1 up is 1 only. Since it is a binary semaphore, 1 up is 1 only. It will enter critical section. When it is running critical section, preemption is occur. Another process comes and try, that is also enter critical section. So every process would be in a critical section. Yes or no? So it won't satisfy the mutual exclusion in that case. Sometimes again. So like this statement 1 is replaced by V of x, then what is the maximum number of process would be in a critical section? They can put it. So I can say that cases mutual exclusion not guaranteed, progression would be there, bounded weight Still guaranteed, because no process will be blocked now. So no deadlock at all. But mutual exclusion would not be guaranteed here. I hope you understand this code. Fine. Some little variation of the code will observe it. Little variation of the code will observe. Look. So binary semaphore initialized to t equal to 1, s equal to 1. There are two processes, P1, P2 are there. P1, P2 are there. Now tell me. So now statements like no mutual exclusion is guaranteed. Second statement is a progression. Progression is guaranteed, and third one is the bounded weight is guaranteed. Bounded weight is guaranteed. So what about deadlock? Deadlock, will it lead to deadlock or not? This kind of question is can ask. So now what do you have to check? Just look at this. Look at the process P1. There are two process P1, P2, and they're trying to access the critical section enclosed by the binary semaphore operations. Now, so ready queues contain process P1, P2. There are two processes only, right? So let's run trace out. Suppose now if I schedule the process P1, so statement 1, statement 2, statement 3, statement 1, statement 2, statement 3. Fine. It will run the first instruction. So t value, what is the p? P of t. T value 1. 1 down, 0 successful. So now it can enter in critical section or not. So first of all, allow one process to enter in critical. Case number 1, allow one process to enter critical section. Apply preemption. So critical section. 2 is what? Critical section. Okay. During this critical section, suppose preemption occur. Then at time t2, process P2 will come. It will run the first statement. What first statement? Down on yes. 1 is 1 down, 0 successful. 1 down, 0 successful. So this will also enter into critical section or not? Yes or no? This will also enter in critical section. Yes. Now I can say mutual exclusion is not guaranteed. Yes or no, all of you? Mutual exclusion is not guaranteed because this also enter. What about progression? Progression is guaranteed here. Why? Why not? Because when critical section is free, if any process tries, it will enter the critical section. Nobody stops. No, you have to think. Suppose process P1 run, assume that process P1 run, P of t, yes, done. So let's think about progress, ma'am. So process P1, if I not apply the preemption, suppose P1, P2 done, then so wake up t. Suppose wake up t. So yes, because wake up it is no relation to this one, right? It can wake up to t only, its own value will be there. So progression is guaranteed, bounded weight is guaranteed. What about deadlock? So deadlock will not happen here. Deadlock will not happen. If the mutual exclusion is not guaranteed, so like occurrence of the deadlock will not happen because we are allowing more than one. Happily, no blocking mechanism. Block will not happen. See, same variable they are using, right? P of t. So use critical, wake up the same variable. Wake up it. No relation. One is not blocking the other. So now we understand. Mutual exclusion not guaranteed. Progression guaranteed. Bounded weight is guaranteed. So deadlock will not occur. Deadlock will occur. So like, will it lead to deadlock? Will it lead to means no, right? So no deadlock will be there, right? Yes or no? Yes. So this way understand. Suppose if I want to ask one question here, to ensure the another question with this one we can frame it. To ensure the mutual exclusion, what must be the initial value of t and s value? Tell him. Think and answer it. What must be the initial value of the semaphore or initial value of semaphores to ensure the mutual exclusion? Mutual exclusion guaranteed. I want to guarantee the mutual exclusion. What must be the initial value of t and s? So because what is a problem here? Please understand. What is the problem? Suppose if I take t equal to 0, then this get blocked, and s equal to 1, if I take 1 down 0, this will enter critical section, it will wake up s only. So it is not allowed. No, entire code need to be modified. No, because there is no any common variable here. There is no, suppose if the t is given or s is given here, what we can do is one thing can be blocked, one thing is allowed. But in this case, what is happening? Simply, so mutual X will not at all guaranteed here. Simple thing. Other variation will observe. Other variation will observe here with this code. So binary semaphore t equal to 1, s equal to 0 is there. So now p of t, b of s, and p of s, v of t is there. Yes, there's a common thing shared here. You ask, now tell me, all of you. So does it guarantee the mutual exclusion? So does it guarantee the mutual exclusion? Check, all of you. Does it guarantee the mutual exclusion? Second question, does it guarantee the progress condition? Third question, does it guarantee the bounded weight? And the fourth statement is, will it lead to deadlock? Will it lead to deadlock? Yes. Think all of you and tell me now. Ready queue has two process. That is process P1 and process P2 at time T0. Suppose process P1 if I schedule it. Statement 1, statement 2, statement 3, and statement 1, statement 2, statement 3. Fine. Now suppose run the process P1, statement 1, instruction 1. What is there? One P of t, 1 down, 0 successful. Process P1 successfully done, then it enter critical section. What I mentioned? Allow one process in insert critical section and apply the preemption. Then process P2 comes at time, suppose T4, assume that. So T2. So instruction 1. What instruction 1? So P of S down on S. What is down on S? Down on S is 0 only, 0. So this is blocked. Not allowed. It is not allowed, right? Hence, I can say mutual exclusion guaranteed. Yes or no? Yes. Suppose if I continue this one, at time T4, process P1 comes again. It will run the critical section part. Then it will run the third statement. What is third statement? V of S. Getting my point? V of S. It run the V of S. So now V of S now wake up. So S well becomes 1 here. S becomes 1. Then complete. At time 6, if process P2 comes, what a process P2? P of S, it will like 1 is blocked, right? 1 is blocked. S value is there. Now what happens here? So you have to run same. So because same statement you have to run. Previously I said the next statement. Please check it again. So P2 is there. Like first it has run the P of S down, blocked. Like S value got 0, 0 down, 0 blocked. Now we are wake upping. So now sorry. So we are wake upping, right? So we are wake upping, nothing but you understand now. Process P2. What a process P2? So this statement already over, right? It will enter into critical section. So who is enter into critical section? So process P2 enter into critical section, right? Now suppose here preemption occurred. The process P1 comes. What P1 value? P of t down on 0, blocked. P1 will block. So hence I can say progress mutual exclusion guaranteed. So now suppose, so the process P2 run the critical section, run the third statement. What is third statement? V of t. Okay, getting my point. V of t. Are you able to understand? V of t is there. Here, like one thing just now I would like to say. So what happened? Process P1, process P2. So it will run the same statement because it is blocked, right? S1. So S1 is now 1 down 0. Statement 1. Then enter the critical section. Run third statement as 1 down 0 successful. 1 down 0 successful. Like getting my point? 1 down 0 successful. But you know what I said to all of you? So what I said the point all of you here, process P2, like carefully observe. So process P2, what happened? Process P2, look at process P2. Statement 1, P of value 0 down 0 blocked. When process P2 got, then it will get the same statement, second instruction only. It will go directly see critical section. So once critical section work over, it will run the third statement, wake up in T. Now T becomes suppose 1. Now it becomes 1. Getting my point, all of you. Now look this, all of you. Suppose process P2 again. So is completed, right? It is completed. Now who is blocked here? Process P1. P1 also completed. Suppose at time T8, process P2 also got chance on that. P2 only got. Then repeat, if I repeat process P2. What is S value? What is S value? S value is 1. Made it 1. 1 down 0, successful. So successful, it enter into critical section. It enter into critical section. Please understand. Critical section. It is in a critical section. Then what happens here? But what happens here? Now when process P2 again got second, again if you repeated, so S value must be 0, then only will enter not, right? So that means you understand here, S value was, how much was there? It was 1. Means when it is run here second time, you understand, when it is run the second instruction, nothing but it will run the first instruction, then only it will run. So it made into 0 only. Now this will go into block state. It is going to block state. So second instruction will not run, because what happened, whenever process P2 got unblocked nothing but this operation need to be performed. S value it made into 1, right? 1 down 0 successful, enter the critical section, made the V equal T, then again it will comes back. Then S value will be 0, right? 0 down means blocked, it will block it. Now process P1, so P1 start. P1, what is the P1? Down on T. T value 1 down 0 successful, right? So mutual exclusion anyway guaranteed. Look at the progression. Is there any chance progression not going to be guaranteed here? Is there any chance progression is not going to be guaranteed? Look. Suppose first if I schedule it, now I woke up, VT woke up here, right? Then when you woke up this VT, nothing but this can be down, successful, right? Is there any chance? So not occurrence. Progression means what? If the critical section is free, somebody not allowing to enter the critical section. So let's take situation. Suppose first initially P1 only we run. P1 T equal to 0, T equal to 1, 1 down 0 successful. Preemption occur, assume that it is in critical section. You try to enter in this one, this won't enter, because what happens here, we are gaining mutual exclusion. Fine. Then it is suppose wake up. It is wake up. Getting my S equal to 1 only there. Now please understand. Now if suppose P2 has not run, situation, yes, you have to think carefully. Suppose there are two processes only there. Process P1 first run. P of T value 1 down 0 successful, enter the critical section, make the S equal to 1. Made the S equal to 1. Okay. Wake up the P2. P2 is not ready queue only, but again process P1 only schedule, assume that. Before P2, P1 only be scheduled. Then what happens here? Process P2 will run the first instruction, P of T. T value almost 0. 0 down, it will get blocked. It will get blocked here. So it is not getting interested. Suppose P2 is not interested to enter the critical section. If the process is P2 is not interested in critical section, then it is going to be block state. Now if it is not run, what happens? It may not satisfy progression. But since I did not put the while loop, there are only same code need to be run, right? Suppose if I put it while loop here, if I put it while 1 and while 1, suppose if I put it while 1 and while 1 here, suppose add it this point, so definitely is not going to be guarantee the progression. But since I did not put the, please understand, I did not put the, I hope you understand my point. So single lines of the code is there, single line of the code is there, right? Single line of the code is there. If second time also process once execution over, again process P1 only schedule, it get blocked, and ultimately process P2 only should run it. Ultimately P should run, because ready queue having P2 only. So no repetition, no while loop is, while 1 is there. So definitely this will guarantee the progression. Bounded wait also guaranteed, it will not lead to deadlock. This understand. Will it not lead to deadlock? I hope you understand my point. Okay. So look into another point here. Another point we'll observe. Another things. Look at here. So binary semaphore or T equal to 1, S equal to 1, process P1, P2 are there. Now critical section enclosed by T of S, V of S, and S of P of T, P of S and P of T, and T of S like this is there. As I mentioned, all of you. So this code definitely guarantee the mutual exclusion, and progression also will guarantee, and the bounded wait also guarantee if that queue is implemented with FIFO. But there is a problem of deadlock, please understand. Reason I'll tell you. Usage of semaphore operation, if you see T of S is there, like here is S of T is the opposite is there. Will it lead to deadlock? Definitely this lead to deadlock, please understand. So this lead to deadlock, all of you please understand. This leading to deadlock here. So one important point you have to notice, any variables are there, suppose semaphore variables a comma b comma c is given like this. What order of sequence will lead to deadlock? Please understand. Suppose one X process is there, like suppose X is a process, Y is a process, assume that Y is a process. Okay, there are two processes are using semaphore variables to enter the critical section. Getting my point? Suppose P of A and P of B, please understand, P of C is there. Okay, this one P of A, getting my point, P of C, P of B. Okay, will it lead to deadlock? If I ask question, will it lead to deadlock? You see A, B, C is there, A, B is there, yes, A, B is there, A, B is there, A, C is there, A, C is there, A, C is there, like this. Getting? C, B is there, here B, C is there. Please understand. This may lead to deadlock. Let us check whether it will lead to deadlock or not. As I mentioned, right, order should be same only. If any opposite order is there, that will lead a cycle. Like, see, BC, CB, it may form a cycle, right? So this may lead to deadlock. Let us observe. A is there and followed by C is there, followed by B is there, right? Let us observe. So for checking this one, what you have to do, all of you please understand. For after each instruction, apply the preemption. Whether this code lead to deadlock or not, what you have to do? Statement 1, statement 2, statement 3. After execution of each statement, apply the preemption. Then we'll come to know whether lead to deadlock or not. There are 3 binary semaphores which are initialized to 1. All are initialized to 1. Fine. So process X started. Statement 1. What is statement 1? So as I mentioned, A equal to 1, comma, B equal to 1, comma, C equal to 1. P of A, 1 down 0 successful. Apply preemption. Getting? So run Y. What is the Y? Instruction 1. So P of A, what is P of A? 0 down. P of A, 0 down, 0. So this will block. Blocked. Getting my point, all of you? Are you getting my point? So P of A, first I run. A value 1 down 0 successful. Enter the second statement can run. But what I did? Second statement I after first statement only I run, apply the preemption. Second statement I got P of A. What is P of A? A value 0 0 blocked. Then after that X value. Second statement, what is second statement? Down on B, B value 1 down 0 successful. 1 down 0 successful, right? Successful. So if I preempt also, process B won't come, process Y won't come, process Y already blocked, right? So let run suppose third statement. What third statement? So down on C, C is what? 1 down 0 successful. Enter the critical section or not critical section? No blocking. Case number 1, when I apply 1 after each instruction, this case number 1 not lead to deadlock. Let's work out the case number 2. Case number 2 for this same thing. Okay. Process X comma Y and A equal to 1 comma B equal to 1 comma C equal to 1. Getting my point? Getting my point, all of you? Now run the process X. What X? X is P of A. A 1 down 0 successful. Run first. Let run second instruction also. What is second instruction? B value. So B, what is B? 1 down 0 successful. 0 successful. Second instruction over. So third instruction, if I write, will enter critical section. Just before going critical section, let us preempt it. Here. Preemption occur. Assume that. Y operation. Y. So statement 1. What is statement 1? A value, right? A value. P of A. A value how much? 0. Getting my point? 0. 0 down. 0 block. This is blocked. So only 2 processes are there, right? Only 2 processes are there. So one is blocked. Other is allowed to enter critical section. Nothing but this code will not lead to deadlock. This code is not leading to deadlock. Because both are sharing same variable starting one. If there is a third process also there using same semaphore value, I understand this C is up first side. C is on first is there. Like AC CA is there. Then definitely that process is going to be blocked like this. You have to check it like this. And sometime how the question they will ask, what order of this semaphore operation you need to keep for these processes so that will not lead to deadlock. will not lead to deadlock. So straight away what you can understand, some elimination you can do it. My suggestion, some elimination you do it. Like now as I mentioned, here BC is there, CB is there, we got a doubt, we tried, so not leading. Suppose here AC is there and CA is there, assume that. Here AC is there, right? Here CA is there, what happens, CA is there, what happens here? Now when you try Y, C becomes what? C, suppose you just, let us work out this only, like, let us work out case number 3. Case number 3, process X and process Y is there and sharing A equal to 1, comma, B equal to 1, comma, C equal to 1, binary semaphore. These are the binary semaphores. P of A, getting my point? So P of C is there, assume that. This is P of B and P of ABC, right? ABC. Then P of A is there, P of B is there. Look this, what is there? AC, CA is there. Okay, BC, CB is there. AB is there. Fine. So let us work this one. Like, what is the conclusion? We can do it like this. Suppose if I schedule X process, statement 1 if I run, what is statement 1? P of A equal to 1 down 0 successful, 1 down 0 successful, getting my. Suppose if I apply the preemption here, then you run the process 5, 1 instruction. What is the P of C equal to 1 down 0 successful. This also preempted as in that. Again X comes, second instruction. What is second instruction? B. What is the B value? 1 down. 1 down 0 successful. Suppose apply preemption. Then again Y comes. What is second statement? What is second statement? What is second statement? Y. P of A. What is A value? 0 down 0. It is blocked. It is blocked. Then run. Then leftover process X only. What is X value? Third instruction, right? Third instruction. What is third instruction? Third instruction. 0 down 0 blocked. Please understand, it is blocked. So both are blocked, nothing but this order will lead to deadlock or not. This order will lead to deadlock or not. Deadlock, yes. Some questions, MSQ question also can frame. Means, what are the following options which so what I am trying to say here, suppose here, like the MSQ question can be framed here. Like here ABC given, CAB given. Like this, many 4 orders are there. Which of the following? What are the orders which will lead to deadlock? They can ask. Or another question, direct straightforward question. Which of the following option will not lead to deadlock question? I hope you getting my point here. So for getting doubt, see, if any such options are there, AC, CA is there, like AC, CA, like starting only opposite, definitely that lead to deadlock. One of the option you need to find out, there won't be like opposite order, there should be some sequence, then definitely that is lead to not leading a deadlock, basically not lead to deadlock. That's why you can identify the options. These types of questions several times I have seen. Some other type also we can expect. They give a 1, 2, 3 process would be there. 3 process would be there. Now I want to generate this order of sequence. Example, BCA, ABC something, this order I want to generate. Then what order of semaphore operation need to be keep? They will ask. Means what is the initial value of semaphore variable so that this order only will print it. So you have to observe clearly what you want to print it, that value should be 1, like that you have to check it. Look at another question. Interesting question. Suppose 2 process P and Q are there and mutex is initialized to 1. So P's code is given, Q's code is given. The string generated by the 2 process dash. Many times I've seen a question like this. Many times I've seen a question like this, What string is going to be generated if I execute this 2 process? What string is going to be generated if I execute this 2 process? Let's work out. So ready Q has a process P and Q. Suppose if I schedule a time 0 process P, it will run these statements. What is statement? Look this one. Let me name it, this is statement 1, statement 2. So statement 3 like this. Okay. It is printing 1, it is printing 0. If I run P, what is the P? Wait on mutex. Mutex file how much? The mutex. So mutex is initialized to 1. 1 down 0 successful. Statement 1. It can go on print which value? Which value? It is printing 1. So let me take the outputs here. Outputs. 1 it will print it. Fine. signal on mutex. Signal nothing but what happens? So it will be 0. So it will make 1. So second and third over. So now see, it is a like while 1 is there. So you observe while 1. So this process can repeat n number of times, nothing, right? If I repeat n number of times, 1, 1, 1 like this, 1 star will print out or not? It will print 1 star or not? Yes. Suppose if I schedule the process queue. So statement 1. So again wait on mutex. Mutex is 1, down 0 success, print 0, signal mutex like no. This also going to be print like if I run 1 to comma 2 comma 3, it will print 0, 0, n number of 0, nothing but 0 star will print it. Yes or no, all of you? Yes or no? Other possibility you see, other possibility. Suppose allow process P1 under mutex print 1, getting my point, print 1, once over then jump to Q. Alternative. So first one time you run P, then another time Q. Then QP, PQ like you can run it. So nothing but can I say, it will print 0 if you run Q1, 0, 1, 0, 1 like this will print, or 1, 0, 1, 0, 1, 0 also will print, right? Yes or no? Otherwise 0, 0s, 1, 1, 0, 0, 1, 1 possible, 1, 1, 0, 0, 1, 1, 0, 0 are possible. All the strings are possible. All the string nothing but can I say 0 plus 1 all. What are the options are there? So 1 0 star 1, 1 0 1 0 star, now 0 1 star. So now 1 plus 0 star. So I can say option D is possible. All 0 1 alone zeros will print, alone ones will print, 1 0 we can get it, 0 1 we can get it, 1 1 0 0 0 1 all possible will get. I can say 0 plus 1 whole star, this will print ma. So this way you can check the options ma. Fine. So now let us look into the, so let us look into other topic, that is deadlock. So deadlock. So what I am suggesting from the IPC synchronization, so go through first all the algorithms, all the algorithms, observe the code and trace out the code like how to check the mutual exclusion, how to check the progression, how to check the bounded weight, these are the things. Another type of question will be that's usage of the semaphore variables. Other type will be also sometime they give us some code x equal to x plus some computation they'll ask what is the minimum value it will produce, what is the maximum value it will produce, how many distinct value it will produce. This possibility also they'll ask. They'll run the two programs. If I run this concurrence manner, these two programs, what is the minimum maximum value will produce? This type of questions also we can get it. Getting? So coming into deadlock, all of you please understand. Coming into deadlock, there are two things only you need to observe, all of you please understand. One question will be under deadlock prevention, and another question we can expect deadlock avoidance case. Avoidance in this case we can observe the Banker's algorithm. In this case we can expect the question from Banker's algorithm. I hope you understand. Fine. So now these are the numerical type question we can expect deadlock prevention under Banker's algorithm. Other theoretical questions also we can expect, like they can ask. So we right, we have various strategies for a deadlock prevention, deadlock avoidance, deadlock detection and recovery, right, and ignorance, deadlock ignorance. Under deadlock prevention means there are 4 necessary conditions we know. Like how we can preempt it, prevent it. One of the necessary sufficient condition need to be dissatisfied. So regarding this question, they can ask the statements. So regarding this points, characteristic, they can frame a question, theoretical question that you have to read it. Fine. So now under a deadlock prevention case, a numerical question they can frame. Let us see these two numerical type questions. So let's have some 10 minutes break before going to discuss this thing. let's continue the remaining things, like what I was trying to say. From deadlock, there are two types of questions we can expect, which are numerical point of view consideration. So deadlock prevention case one question, and deadlock avoidance, like that is a major important thing. Banker's algorithm. So if the theoretical question is framed from this area, so as I mentioned, under prevention case, there are statements are there. So necessary sufficient conditions of the deadlock, we need to decide one of them. So regarding that, they can ask question. So let us move into the question under a deadlock prevention. What type of question we can expect here? What type of question one expect? So one question I took it here. All of you look this. Consider a system having n resources of the same type. These resources are shared by three processes P1, P2, P3, which have a peak demand of 9, 11, 14 respectively. For what value of n deadlock will not occur? What value of n deadlock will not occur? This is a question. How many processes are there? Note of it: process P1, process P2 and process P3. Their maximum demands, the maximum need 9 resource and 11 resource and 14 resources. The consider system having say n resources of the same type. Same type, nothing but what? What is the same type? Same resources. Like example, printer is a type, resource type. Tape drive is a resource type. Now printer is a resource type. If I take same type, there are copies, 11 copies required, 9 copies, 11 copies, 14 copies, like this. This is a demand of each of them. Now what is the question they are asking? What is the question asking? Which peak demand is given? For what value of n, then the system will not lead to deadlock here. So now whenever this kind of question is asked, please understand. So now like deadlock prevention, what is there? We have to break the hold and wait condition, right? Prevention. So what do you do? Just simple thing I am just trying to say all of you. Look at their demands. Allocate the process 1 less than their demands here. Are you demanding 9, right? You allocate 8. This 10. This is 13 you allocate it. Okay. So total how much is there? This is 23 plus 8 is 31, right? 31. So now need, if I look at the need, remaining need, are they satisfied in this moment? If I suppose n value 31 is there, if n value is 31, are they process satisfied? Each process required 9. If they get 9 only, it will satisfied. Otherwise situation, understand, in this moment situation is like they are holding, waiting for a resource. Holding 8 resources, waiting for 1 resource. It is holding 10 resources, waiting for 1 resource. It is holding 13 resources, waiting for 1. Hold and wait is there, right? Hold and wait. What we can do? 1 extra allocate it. Allocate 1. What happens? So 8 plus 1, 9. So 9 completely given. So process happy, then it will execute and release the 9. Then with this we can give 1, we can give 1. So you understand, 31 plus 1 extra if you give it. So this is a value, minimum value should be 32 will be there, for which no deadlock will happen. This is a minimum value of 32, no deadlock. But what about, sir, 31 if it is there? 31 is there, it is a deadlock. Please understand, this question can be framed in reverse, like reverse nothing, other type question they can frame. What is the maximum value of n? This will lead to deadlock. System V to deadlock will be 31, maximum value. So why 31 is a maximum, sir? So why 31 is a maximum? Why 31? Suppose 30 if I give, what happens? If I given 30, deadlock or not? Deadlock or not? If I give 29, also deadlock. So like no minimum, maximum. If I give 32, what happens? So it will not follow deadlock. So now 31 is a boundary for me, system can lead to deadlock. If I given 32, no deadlock. That's what I said. 33, no deadlock. If I give 50, no deadlock, like this. So that's what I asked. Minimum value to ensure the deadlock free operation is what? 32. What is the maximum value to cause the deadlock is what? 31. This way you answer it. So generalization, how we can generalize it, sir? Suppose example, please understand. So n processes are there. N processes are there. Please understand. N processes are there. Getting my point? Each process, its peak demand. Its peak demand. Each process peak demand. So demand. Please let me take SI. Okay. N process and suppose the particular process Pi if I take it. So let me write otherwise. So I will write. n processes are there. Process pi is a process. Pi is a process. Its peak demand is peak demand. Demand is SI. Ith process required SI demand. So now question is that what is the minimum value of M? So I am taking what is the minimum value of M. I am taking M is a resource. So like no, M is a M number of resource of same type. Let me take R is a resource type. Suppose if I take what is the minimum value of M, I am asking. Let me take R equal to 1. 1 is the resource type 1. One type of resource having M copies here. How many minimum number of M is required to ensure the deadlock free operation? So previously was there with this extension generalizing all of you. Are you able to understand? What is the minimum value of N? Then system will not lead to deadlock. It's a question. And what is R? R is a resource type, printer. So M copies of printer is there like this. How many minimum copies of printer required so that deadlock will not occur? That way you understand. So look at the processes. Process. Getting my point? Process and maximum their demand. See, process P1, process P2, process P3, like this N processes are there. What I said the demand is S1. Pi is the demand is SI. P1 S1, S2, S3, like this Sn is there, right? Sn is there. What I said you all of you, how allocation should go? Demand minus 1 you have to take. Suppose you demanding S1, right? S1 minus 1, S2 minus 1, S3 minus 1, like this Sn minus 1 you have to do it. Then what I said you like now. So like this allocation, if you take summation, so you have to take allocation, total allocation much. So if I take in terms of summation, I equal to 1 to N, right? N or N process, summation of S1, S2, S3, Sn. So I equal to 1 to N. Si can I write it? I can write. How many ones are there? N's are there. N ones are there means minus N will be there, right? Yes or no? So this is the total allocation for which what I said here. See. So need minus 1 allocated plus 1 extra I given, right? Plus 1 extra I have to give it. So this is a M I should write it. Let me write it. This is a M. Getting my point? So minimum number of M is required. Summation of I equal to N to S, that is Si minus N plus 1. Suppose this, if I simplify it, M plus N equal to summation I equal to 1 to N Si plus 1. Can I write Si plus 1? Then so this part, suppose this part if I want to remove it, what happens here? So this we can rewrite as summation I equal to 1 to N Si should be this demand, like a summation all demand. Si is our demand, right? Demand only, right? Demand should be less than of M plus N. So this is a condition I can say. So it will not cause a deadlock. This will not cause a deadlock now. So now simply summation of all their demand less than of M. What is M? Total number of resources available plus total number of processes. So this will give. So in like now what are the minimum, suppose anything is not given, other thing we can find out. Nothing, like no, suppose M is not given, M we can find out. N is not given, N is we can find out by using this expression. I hope you understand my point. This is a generalized thing we can understand now. Simply look at their demand, allocate less demand minus 1, demand minus last one process, one resource extra give it. So that will not lead to deadlock. If you not give that extra, that will lead to deadlock. This way you understand. Fine. So look at the another question. So this question, see. So I am just going for Banker's algorithm. Consider the following resource allocation graph with a 3 resource R1, R2, R3 and 4 processes P0, P1, P2, P3 is there. Now find the safe sequence asking here. So understand please. So I hope you studied the Banker's algorithm. The Banker's algorithm, the major thing what you have to understand, we need to find out the safe sequence. If you are able to find out the safe sequence, system is safe. If the system is in safe state, no deadlock. If not able to find out the safe sequence, system lead to unsafe state. Unsafe state lead to deadlock, it is not a deadlock. unsafe state is a lead to deadlock, means possibility of deadlock will be there. That's what observe. So you know, right, Banker's algorithm requires some prior information of the process demands. Based on the state of information only, we are going to allocate it. Like the state information, nothing but I said safe and unsafe state. Safe state, nothing but need to find out the safe sequence. Like now, resource allocation graph is given. Now need to, they are asking to find out the safe sequence. So quickly, what you can take it here, process. Their maximum demand find out, resource R1 type, resource R2 type, resource R3 type, demand find out. And allocation also might be done, allocation resource R1, resource R2, resource R3. The remaining need requested, right, need also need to find out, need we need to find out. So resource R1 type, resource R2 type, resource R3 type. Now next vector is what, available, currently available of resource R1 type, resource R2 type, resource R3, and total resources also need to find out. So total resources, total, let me write here. Sorry. Total resource of each type, resource R1, resource R2, resource R3. So that how to check? You see that resource R1, how many copies are there? Dots are there. Dot 1, dot 2 dots are there. Like 2 dots are there. Resource R1 having the 2 copies like this. Understand? 2 copies are there. Getting? Next. Resource R2 having how many dots are there here? 1, 2, 3. 3 dots are there. So 3 are there. Fine. So resource R3 type, how many dots are there? Inside, you see inside 2. You know, right? Single instance and multiple instance representation. So single dot indicates single instance. The resource having the multiple copies, nothing but there would be multiple dots should be there. Understood? How many processes are there? P4 process. Let me take it different color pen. Process P0, process P1, process P2, process P3, right? There are 4 processes. Now maximum demand of each type, how to check it? Process P0 go, maximum demand, how many it is demanding? Process P1, P0, right? P0. You see, process P1, you have to look at the arrows here. So maximum not required, this maximum vector if you remove allocation only, you see P0. P0 we have allocated R1 type. So look first R1 type, R1 1 we allocated. Allocation you see, and R3 1 we allocated, then R2 no. So R1, R3 we allocated. Let me take it here. 1 copy, 0 copy, 1 copy like this. Allocation plus request also it becomes a demand only. So let us minimize that work. Process P1, R1 1 type allocated, R2 1 copy allocated, right? R1, R2. So R1, R2, this is 0. This is what allocation. Yes or no? You see process P1 from R1 1 copy, from R2 1 copy, R1 1 copy, right? Process P2 is R2 1 copy is there, bus. Process P2 is R2 1 copy is there, right? So like this, you understand? Am I right? R2 process, which one process we did? Process P2. Process P2C 1 copy we allocated. Process P3, 1 copy here. That's it, right? 1 copy only, right? It is requesting only. So 1 copy of what? 1 copy of R2. So this also 0, 1, 0, right? So need nothing but request. Look at P0. P0 putting a request to 1 copy of R1. So nothing else, right? One copy required. So 1 copy. What about P1? Process, sorry, we written for P1, right? P1 is 1 we requested, right? 1, 0, 0. This is for 1, 0, 0. I will modify P0. Look at the P0. P0C putting a request to R3 1 copy and R2 1 copy. R2, R3. R2 R3 like this, you understand, this is not there. And allocation was P0 allocation, 1 copy from R1, 1 copy from R3. Yes, fine. So look at for P2, process P2, process P2. Process P2 requesting 1 copy of R3. Yes or no? R3 and anything? No, R3 only. 0, 0, 1. 0, 0, 1. Right? Yes, next. Process P3. P3 only, P3 left over. Process P3, 1 copy required R1, 2 copies required R2. R1, R2. So now 1, 2, 0 like this, you understand. Right? So look at the allocation. Look at the allocation. What are the allocation happen? 1, 1, this is 2 we allocated, 0, 1, 3 we allocated, 3 we allocated, and 1 we allocated, right? Now 2, 3, 1 we allocated. How many are there? 2, 3, 2 are there. 2, 3, 2 is there. Means leftover will be available, will be out. 0, 0, 1 will be there. 0, 0, 1 will be there. I hope you understand now, all of you. I hope you understand. See, this allocation, what you can, how to get the maximum? This you add it. What is the maximum? 1, 0, 1 will be there. So this is 1, this is 2 will be there. Yes or no? For this what? 2, 1, 0 will be there. For this 0, 1, 0, 1, 1 will be there. For this, this is 1, this is 3 copies, this is 0 will be there. Like this is maximum demand. Some allocation need is there. Fine. So this way we can understand now, all of you. Now, so what? So double line, suppose if you have a double array syndication, 2 copies required, all of you. This you have to learn from this one. Because, so intentionally I took this resource allocation graph. Normally, you will get a question like this. They will give the process IDs, they will give the maximum demand, they will give the allocation vector also. You need to find out the need. Need we can obtain maximum minus allocation. Then remaining available you need to find out from allocation counted, remove from the total allocation, you get the current availability. Then you start getting what? Safe sequence. Find the safe sequence. But in the diagram is given how to take the data, means I hope you understand. So you have to see like this, you have to understand like the process is there, process, okay, this is a process P1 is there and the resource R1 is there. If this arrow is the nothing but allocated, this arrow is nothing but requested, this requested we call. This we called request edge. This is what allocation edge, allocation edge. I hope you understand. So based on that only we have copied the data. Now see, so we need to find out the safe sequence. All of you need to find out the safe sequence. Currently available how much is there? 0, 0, 1. 0, 0, 0, 0, 0, 1. Which process can be satisfied? You look at the needs. 0, 0, 1. Yes, only process P2 can be satisfied. P2 can be satisfied. Do we have option? P2. So now eliminate process. Option A, option D can be eliminated. Option C or option B possible, right? Chalo. Now process P2 will start. And if I give 0, 0, 1 to him, he will release this many, right? How to calculate? I mentioned, like you studied from classroom also. Available can be obtained after this process P2. Available equal to available plus current allocation. What is current allocation? 0, 1, 0. If you added this value, how much will get? This still 0, 1, 1 I will get, like this 0, 1, 1 I will get. With this 0, 0, 0, 1, 1, which one we can satisfy? Process P0 can be satisfied. Process P0 can be satisfied. Look at the options now. P2, P0. P2, P0, both are there. So you cannot eliminate. Go and see now. So P0, if I allocate 0, 1, 1, he will release 1, 1, 2, right? How we can obtain? Simply current available equal to available plus allocation, you do it. So 0 plus 1, 1, 0 plus 1, 1, 1 plus 1, 2 will get it, right? 1, 1, 2. Which process you can satisfy? So can I satisfy P1? Yes, you can satisfy P1. We don't have other option, right? Can I satisfy P3? No. P0 already over. Then what is the P2? P2 already started, right? So 2 over, then P3, P1 only possible, P1. So option C, P2, so now, so P2, P0, P1. So now P1 only we got, right? So directly I can select the option A is our, C is our right option. Chalo, continue process P1 if I do. So process P1 if I do, where is the process P1? Yes, this will comes. allocation available equal to available plus allocation, right? Yes or no, all of you? Now what happens here? P2, where is P2? P1, right? P1. So 1 plus 1, 2, 1 plus 1, 2, this is 2, 2, 2, 2 will get it. Yes. So 2, 2 nothing but P3 can satisfy, P3 can be satisfied, right? So after this P3 working, 0 plus 0, 1, 0, you have to add it. 2, 3, 2 will get it. See now, we got a safe sequence and original value, we got it or not? Original value, we got it, yes. So I can say, now this state information is safe. So we got the safe sequence like this. I hope you understand. So majority time, all the previous paper which I see, they given like this only. Process ID will be there, maximum vector will be there, allocation vector will be there. You need to find out the need vector. You need to find out the available value. Sometimes they say available value also they give you directly without giving total. They can give directly this value. You need to find out the safe sequence. Sometime they can be more than one safe sequence, right? Yes or no? They can ask how many possible safe sequences. Otherwise, which of the following is not a safe sequence? This also possible, ma. So I hope you understand. Chalo, we'll move to other topic. From again repeating from deadlock, one theoretical aspect means for like comparison between all the strategies, right? Deadlock handling strategies. The second one is like deadlock prevention case which you took the previous problem, that type of question, and bankers based algorithm, this type of question. There is a possibility of making 2 mark question 1 or 1 mark question mark. There's sometimes 2 questions, sometimes 1 question. 1 question is framed, it can be 1 mark question, it can be 2 marks question we can expect from this area. Fine, ma. So let's move on to the next topic, is memory management. Let's move to the next topic is memory management. Memory management. So memory management. So the memory management topic is concerned, like majorly we need to focus on memory management, management techniques, memory management techniques. So because what is the studying of the memory management? What is the purpose of to study the memory management, ma? You understand, operating system creates such an environment for executing the programs. As per the what? Van Neumann architecture, programs must be stored in a main memory prior to the execution, right? You have to keep this program in main memory for further execution, right? Under multi-programmed environment, we have to keep more than one process in main memory, for which memory need to be partitioned, right? Memory need to be partitioned. Getting my point. The way of performing these partitions depends on the memory management techniques. There are various memory management techniques, ma. There are various memory management techniques. This basically classified into one is contiguous. So contiguous allocation, contiguous allocation. Second one is the non-contiguous allocation method, non-contiguous. Non-contiguous allocation. Please observe, all of you. Please observe. So second one is what? Second one is the non-contiguous allocation. Non-contiguous allocation. Fine. So now look this, all of you. If I say contiguous allocation means, all of you understand, program is at one place. Program is at one place. Please understand. Program will be at completely one place. Entire program at one place. This we call centralized mechanism also. These are decentralized, means program is distributed over the memory. Distributed over the memory. Means different regions it occupies. It occupies what? So different regions program will occupy. Different regions program will occupy. Decentralized means, you understand, program you have to scatter into some units. Units are thrown entire memory. Sir, how to search? We have to do that mechanism. But under case of contiguous allocation, that entire memory is not partitioned, kept at one place only, you understand. The process start, beginning and ending will be there, then start, execute and complete here. So under contiguous mechanism, under these mechanisms, we have a partition methods, please understand. We have a partition methods. These partitions are fixed partition, and second one is a variable partition. Getting my point? Variable partition. Yes. So when it comes to non-contiguous allocation, this non-contiguous allocation method is implemented by the various approaches. One is simple paging, essential topic, and second one is what? segmentation, and a segmented paging also can be used here, right? So let us observe one of them one by one. Like, so if we consider the first one is a contiguous allocation, contiguous allocation. So contiguous allocation means what I said you, this memory if I take, please understand now. So basically this memory is divided into two parts. One is OS area, this is a user area. User area, further we do the partition. Now after doing this partition, please understand, each partition will be for a process A stored, process B stored, like process C stored, like this. Entire process would be one place only, like this. What contiguous means? Contiguous nothing but entire process would be same only. So these partitions can be same or different, right? This partition can be same or different. Now that's what I said now, partitions are, please understand. So partitions are, there are two types of partitions we can have. One is fixed partition, right? Fixed partition. So fixed partition, please understand, with fixed partition. Second one is what? Variable partition. Second one is what? Variable partition. Okay. One is fixed partition, second one is a variable partition. What does this fixed partition? Please observe. Fixed partition nothing but, so size of the partition is fixed. Now, sir, what about these partitions? Partition can be same size partitions, it can have a different size partitions also. But understand, entire memory is divided into fixed number of partitions only, which are fixed. Example, let's say 100 partition, let's say 200 partition. The 200 partition can be of same size or different size. It can be same size or different size. Getting my point? Now, sir, how to allocate? Very simple. Look at the process size. Look at the process size. The process size, like, please understand. Look at the process size and look at the partition. Getting my? The partition size which is greater than or equal to process size, that partition is given to allocate. It's simple. Wherever the process able to fit into that partition, we are loading. So suppose more than one partitions are eligible to keep this process. Example, some partitions are there. One process size comes so many partitions can be kept. Meaning we understand. Program size suppose 100 KB is there. There are partitions of 120 KB, 150 KB, 200 KB, 300 KB partitions are available. That means 100 KB process can be kept anywhere, right? So which partition should chosen, sir? So we have a allocation policies, please understand. So we have allocation policies. So what are the allocation policies? Allocation policies, you know, first fit you studied, right? Best fit, next fit, worst fit, right? Please understand. One is first fit, best fit, and next fit, worst fit. Yes, based on this also question has been framed. Yes, there was a question previous year paper. If you go and see, there was a question in this. They'll ask some partitions are given, some free blocks. If we run with the best fit, what are the partitions are allocated, what are the partitions not allocated, how much internal memory is wasted. Otherwise, among these policies, which one is the best policy? You understand, all of you. If the space is considered, memory space is considered, the best fit performs well under fixed partition. I am repeating the statement. The space is considered, means space like crucial, right? Memory space is very crucial. Which policy is minimizing the space? Nothing but best fit will minimize the space. In terms of time, the first fit is better, because best fit every time you have to search the best, means smallest free block that is sufficient to accommodate the requested process. Every time you have to search entire partitions. So it will take time consuming. In terms of time, if I talk first fit says that start from scanning from the beginning, whichever empty block is available that is sufficient to accommodate the process is given. It won't search everything. In terms of time, this is better. In terms of space, this is better. That you have to understand. Under fixed point allocation. What I said, this fixed partition, if I say partitions are same size or different size, but number of partitions are fixed. Number of partitions are fixed. Getting my point, all of you. Some points we can observe. For fixed partition. First thing, please understand. First thing, I'll write it like, no, I'll take. Okay. Number of partitions. Number of partitions. Tell me, what number of partitions which are fixed? Which are fixed number of partitions? Suppose second point, if I say, does suffers from the internal fragmentation? If I ask, so yes, internal fragmentation would be there. Why reason? When you do a memory some partition wise, when you do partition wise, and the process comes unequal sizely, then some portion is going to be wasted. That we call internal fragmentation. It suffers from internal fragmentation. Then fourth point. So number of programs, how many programs you can load it? Number of programs loaded will be proportional to number of partitions only, right? How many partitions are that when you can do it? This is inflexible, I can say, inflexible. Inflexible, right? Yes or no? Fourth one. What is the maximum program size possible here? What is the maximum program size? Maximum program size, it is completely depends on the maximum partition size on maximum partition size. It is also limited. Maximum partition size, because these partitions are already made. The partitions are already made here. Fine. So maximum program size you can load under fixed partition depends on the maximum partition size. Yes, Wajid. Hi. So like, no, just I would like to recall this. This is a session, quick revision on operating system. It is majorly focused for GATE 2023 aspirants. Like they are going to write, if you are same 2023 aspirant, then you can stay. Like, no, things are we are going to revise. So you might have made some short note that I am going to revise, like you understand. So almost the first two chapters already we did. Then we are under memory management. I would like to discuss various memory management techniques, their performances, will observe it. You stay for some time, you will understand something. Yes, Wajid. Okay. Look, this maximum program size is limited to what? Maximum partition. It is also inflexible, right? Yes or no? What are fifth point? If I say, does it suffer from external fragmentation? External fragmentation. It won't suffer from external fragmentation. These are the observation. What is the this problem with this? Problem with this internal fragmentation and degree of multi-program is restricted here. You cannot create more programs here. That is completely depends on the number of partitions in the memory only. Am I right or wrong? Wajid, have you studied this fixed partition mechanism? Chalo. So like shortly we look for the variable partition. Variable partition. So the drawbacks from the fixed partition can be overcome here. Variable partition. Variable partition, nothing, please understand all of you. So we won't do any partitions earlier, like dynamically we do the partition based on the process size. Partition done, please understand, partition done based on process size only, So based on process size only. So according to the process size, we have to do the partition here, you have to do it, fine. And here please understand, worst fit allocation policy performs better here. Worst fit allocation policy performs better. Here internal fragmentation will be there here? No internal fragmentation. Is there external fragmentation here? External fragmentation? Yes, it is there. How, sir? So we make a dynamic partitions, right? Dynamic partitions. We see the process size, we can make a dynamic partition. Some situation may happen, process would request some sizes. The size will be available, but that memory is not a contiguous memory. Some different regions is available. You cannot combine those memory to accommodate the process, requested process. That memory is going to be wasted. Those small partitions are going to be wasted. That we call external fragmentation, means some of the free holes that can be satisfied the requested process size, but these sum of holes are not in one place, which are different places. I hope you understand. That lead to external fragmentation. We solve internal fragmentation. Then you understand here, under variable partition, degree of multiprogramming is flexible. Please understand, it is a degree of multiprogramming. Flexible means what? What does mean flexible? What does mean flexible here? Suppose smaller size process, if you create more number of process, you can load it. Larger size process, if you created less number of process, can be loaded here. That's what flexibility. Now see, maximum process size process size or program size would be how much? Proportional to memory size, directly memory size. So one process can be size of the memory here. So for example, entire main memory of suppose 512 KB is there, your process size can go up to 512 KB. It's not restricted to partition size, it's restricted to the main memory size. This is also flexible. This is also flexible. Now what is the problem with this variable partition? Everything looks good because degree of multiprogram increase. If degree of multiprogram increase, throughput also will increase, CPU utilization also will increase. Yes or no? Yes or no? We have flexibility of storing the size of the program and no internal fragmentation. But what is the problem is there here? What is the problem? External fragmentation is there. Am I right or not? This external fragmentation, please understand, external fragmentation can be resolved with the two approaches. One is compaction. One is compaction. What does mean compaction, sir? Simple, see, the memory is there. Suppose here is a free wall, here is a free wall is there, here is a free wall is there. What we can do? This all free walls can be combined at end of the location. This is what compaction. Combining of all free walls into at end of the memory. So that can be used for other process. But it is little costly because hardware support highly needed, relocation required, dynamic relocation. So other approach also we have the non-contiguous allocation. So non-contiguous allocation we do here. So non-contiguous allocation. Here please understand. So this external problem can be solved. As I mentioned, first approach we have simple paging. Yes or no? Simple paging. Second one is segmentation. The third approach is segmented paging. And you understand, to achieve the running of the large program into smaller memory, we use a concept of virtual memory here. That gives a running of the large program into small memory. Yes, Wajid, am I right? Are you able to understand these points? Do you have any doubt? Wajid? Chalo, we'll move on to the simple paging here. First one is a simple paging. Simple paging. Yes. What simple paging says? Simply see, if you see the architecture of the non-contiguous allocation, a process who is running in a CPU, please understand, the process who is running in a CPU, we know, right? It generates the logical address, right? This logical address needs to be translated into physical address, okay? Physical address to access your main memory, right? Main memory. Yes or no? So this memory management unit, there are components will be there. So arrangement of the logical address space, arrangement of the physical address space, arrangement of the memory management unit, and translation. This translation means logical to physical address with help of memory management unit. This memory management unit is implemented by page table, or if I use a segmentation, segment table will use it. If I use a space table, with the help of page table can be translated. If you use a segmentation, we can use a segment table to translate it. This is the architecture, simple architecture. Fine. So you know, right? So paging, like what paging says here, we use a page table. Right? We use a page table. Look this, all of you, how we can do it. So particular process PI who is running in a CPU, okay, generating the logical address. As we know, this logical address will be split into two parts, right? One is P, one is offset. Offset is D. What is a D? Offset, displacement we can say. P is a page number. This page number need to search into page table. The page table, please understand, operating system create a data structure called page table, which assigned for each and every process. Every process which you create in a system having its own page table, like a PCB is there, right? PCB is ID card, it's serving as ID card to a process. Like you understand, every process has a page table also. What page table is contained, sir? This page table entries will be there, This page table essentially contain the frame number of a main memory. you have to take this frame number, pad to this offset value. So this total gives a physical address. With the help of physical address, we can access the physical address space, nothing but main memory. This is a translation, logical to physical address translation. Some address will be there that we will translate in physical address, get the data from main memory. This is the architecture of the simple paging. Where page tables are we are keeping? Page table we are keeping into main memory only. So now in order to access the data, please understand, if I go and directly access the main memory, if it takes m unit is required. With this paging, first you have to get the page table, 1m is required. After that 1m required to access the data, 2m is required, right? Getting my point, all of you? If you use a paging, page table will be there, page table kept into main memory only. Page table is also kept into main memory only. Getting my point, all of you? So first, in order to get the data, first you have to access the page table. Then you have to access the data. 2m is required. So there are two things we have to see: performance of the performance of the paging. If we see, two aspects we have to observe in terms of time, in terms of space. In terms of time and in terms of space. Am I right or wrong, all of you? Suppose. So I am saying that performance of the paging. First what? Temporal things. Temporal nothing but time issues. Time means what? What I am trying to say. So main memory is the main memory. Main memory access m units I am taking. Without any page table, nothing. Simply I can go on to main memory access. Suppose paging concept is not there, m. But if I use a paging concept, you ask, like we call effective memory access time. Effective memory access time with the page table will be, it is going to be 2m. Why 2m, sir? So page tables kept in main memory, you have to access first page table, get the frame number, pad D, you will get a physical address, access main memory. 2m is required. 2m, right? This 2m can be reduced to 1m by introducing the TLB, translation look aside buffer. So let me draw the diagram for that. Let me draw the diagram for that. Okay. As I mentioned, CPU. Okay. Some process we running in a CPU generate the logical address LA. So this we divide into two parts, page number and offset. With the help of page number, we can get the frame number from page table, right? Page table. We get the frame number here. So frame number you take pad with this offset value D from this portion. Okay. This will give the physical address. And with this help of physical address, we can access the physical address space, that is main memory. So this is creating 2m, 1m here, right? I want to reduce this m further, so we are using the TLB here. What is the TLB, sir? TLB is a translation look aside buffer. It has here page number followed by frame number will be there. So D is common, I can pad it. So take this logical address search. So for a corresponding page number, frame number if you have, so now what I can do? So the D is there, D I can pad F plus this D I can pad it or not. This I can connect like this D. Then with this D can I access or not? This is required M. Now understand, this is required C. C is access time. Here C is a much more smaller than M. That is the reason it is reduces to, we can ignore a C value. If I ignore, C is a much more smaller than M. Now take the physical address, P values, search corresponding frame number. If you get a frame number, pad D, you will get a physical address, right? This is a physical address. So once you get a physical address, you can access from main memory. So till the time, how much you spend? C amount of time only you spend. Right? C amount of time only you spend. The C is smaller than the M, so we can ignore that, nothing but M only required. That's what I said, So 2M to 1M I can reduce if I use a TLB, translation buffer. So what TLB having? TLB does not have a data, it have address. Like list of page numbers followed by list of frame number. Like for corresponding page, there is a frame number. That should understand, right? Now, if I want to write the expression like effective memory access time, like let me add. If I want to write the effective memory access time by considering simple paging plus TLB, yes, tell me. Where to access? First TLB. Let's take X is the iterate of the TLB, because Every reference you cannot say that that is available TLB, right? The TLB size is smaller. Some entries only would be there. If any thing you search, if it is it, that I am saying X is a it rate. If it is it, please understand, C amount of time, C plus M is required. If miss occur 1 minus X's, then C you spend already, 1 M required for page table size, other M is required for main memory, 2 M is required. I hope you understand. See, if it is it, so I am making X here, X is iterate of the TLB, X into C plus M will be there. If miss occur here, what is the required now here? C spend already, C plus 2M will be there. I hope you understand this expression. Many times you have seen the paper, they give a page table access on this much, cache access on this much, TLB access on this much. They'll ask average access time or effective memory access time. So this we can use the expression to get it. Fine. I hope you understand now. So now including, please, they can put some cache memory also, they can ask some expression. They can put a cache memory, they can ask an expression. Means once you get the physical address, don't search into main memory, search into cache content. If cache miss occur, then go to main memory. If TLB miss occur, then go to page table, get the physical address, don't search into main memory, first search into cache memory. With this respect also question can be framed. You have to draw the diagram and write the expression. So diagram is always not required, write the expression for that. So that also can be done. So these all the things what spatial, like temporal issues, time. So time can be reduced by having extra memory, that is what TLB. TLB again cache memory only ma. But why we name it TLB? Cache memory only you can call, but cache memory contains generally data. If I say TLB contains addresses it is containing. Getting my point, all of you? Chalo. So other aspect we'll see, spatial. Second aspect is what? Spatial issues means space. Here more concern for page table sizes, page table size. Please understand. Why spatial thing? Please understand. Page tables we kept in main memory only, right? Page table size is the overhead, because when you keep the page table in main memory, so that it will impact on the other data need to be stored. Our pages we need to store, but page tables also keep in nothing overhead to the memory. How overhead, sir? If I take example, let if I take logical address of 32-bit, I am taking old architecture 32-bit. Suppose if I take page size is a 4 KB, if I take, getting my point. Now what is the logical address space? Logical address space is 2 power of logical address, right? Yes or no? Unit is a byte. So 2 power of 32 byte is giving the 4 GB, right? 4 GB. Am I right or not? 4 GB. Now number of pages. So we have to divide into page wise. Number of pages, let me take capital N in logical or virtual address space equal to total 4 GB divided by page size is 4 KB. This giving 1 M. Am I right or not? 1 M only? How, sir? 4 GB can you express 2 power of 32? 4 KB 2 power of 12. 2 power 32 minus 12 is 2 power 20. 2 power 20 is 1 M. So let's take now, suppose if I take page table entry eval essentially contain frame number, suppose 2 byte is there. That's now page table size. How to obtain? How to obtain the page table size? Page table size. How to obtain page table size? Page table size we can obtain. So what page table is containing, sir? Page table containing essentially entries. So there is an entry for each page of a logical address space. How many pages are there? 1 M. 1 M entries would be there. Why, sir? Because, so what is non-contiguous? Program we are dividing pages are distributed over the memory. We don't know where they are, right? That's what for each page there is an entry in a page table. That's what 1 M nothing but 1 M entries will be there. And what entry is containing? Entry contain the frame number information, that is 2 byte information. So 2 MB. So now understand 2 MB is a page table size here. If I created some 10 process, nothing but 10 into 2 MB, 20 MB data required for storing the page tables, not data. This is overhead to the memory. Because see, main memory is a crucial for us. It's a smaller size in terms of secondary memory. We cannot compromise. This need to be minimized. the page table size need to be minimized. How to minimize the page table size? Somebody could answer. So why it is 2 MB? There are 1 M entries are there, 1 million entries are there, 1 million pages. That's what 2 MB we got. Suppose you think it like, no, how we can reduce the page table size? How we can reduce the page table size, all of you? How to reduce the page table size? Please, there are two approaches. I am writing how to reduce the page table size. Page table size is a question. Okay, first one, increase the page size. Suppose, ma'am, here 4 KB is there. Let me take where it is. Here 4 KB is there. Instead of 4 KB, if I take an 8 KB, so it will reduce or not? If I divided by, instead of 4 KB, 8 KB, if I reduce 512 K, can I get it or not? Yes or no? So nothing but when page size increase, number of pages will reduce, nothing but number of entries in a page table will reduce. So therefore we can say page table size also small. Getting my point, all of you? First point, so okay, first point, look this, let me, just a second. We are here, right? Let me move. Yes, okay. Now see. So now if we increase the page size, page table size, I am writing like decreases. This is the line is decreases. Yes, this is one way of reduction. Sir, what happens here? If I increase the page size, please understand. If I increase the page size, page table size, first thing page table decreases. Second point, you understand, internal fragmentation will increase. Please understand. Getting my point? Internal fragmentation will increases. I hope you understand my point. You might have studied. Sir, how internal fragmentation occur? Because we are doing the fixed sizes, right? Under paging, entire program we divided into fixed number of pages. And there is an internal fragmentation last page of each process. Not every process can cause internal fragmentation. If internal fragmentation caused for a process, it would be last page only. So when you increase the page table size, this also will increase it. Sorry, when you increase the page size, this also will increase, that will reduce. So now we have a converse problem. When you want to try to reduce the page table size, internal fragmentation will increase. Sir, what to do, sir, to minimize this one? So first solution is what? Finding the optimal page size. Optimal page size will be, you know, so this optimal page size, P, if I take square root of 2SE is there, already proven thing is there. You might have studied from classroom this one. This will give the optimal page size. The second solution is what? Multi-level paging. Multi-level paging. Getting my point? Multi-level paging. So second solution is a multi-level paging to reduce the page table size. How multi-level paging will reduce the page table size, sir? So first we understood, right? Let us look into the how will reduce the okay, one more point. Actually, here is there, right? Let's okay, look this. Look all of you, ma. So now how multi-level paging will reduce the page table size? Let's see. Multi-level paging. Though you studied, so just I am just giving the glance. Multi-level paging. So let's take logical address. Logical address 32-bit is there. Okay, getting my point. And page size is let's take 4 KB is there, right? 4 KB. Page size is what? 4 KB. Getting my point, all of you. Multi-level paging nothing but paging on page table. Please understand. Paging on page table. So let me take page table entry value 2 byte is there. So now see what happens here. Process who is running in CPU, okay, generate the logical address. How much? Logical address is 32-bit, right? So naturally we have to divide into two parts, right? We have to divide into two parts. One is page number and offset D. What is the offset value? 4 KB, nothing but 12 bits required, remaining 20 bits required of page number only. Now understand, one single page table is there. How many entries will be there here? How many entries will be there? How many entries will be there? 20 bits, nothing but 2 power of 20. So 20 bits, nothing but 2 power of 20. 1 million entries will be there. This is a large page table. So now multi-level page is nothing but what you have to do. This page table is there now. This page table you have to divide into pages. You have to divide into pages like this. You have to divide into pages. Those pages you have to keep into main memory. Then how it will reduce, sir? So means let us observe this one, how it will do. So this one only I am taking like this, you know. Let me take the page size. Page size. So I want to do paging on page table, right? I am taking page size for a page table. Page table will be 1 KB. I'll take it 1 KB. Fine, 1 KB. Now see what happens here. First level paging will happen like, you know, CPU process we running in the CPU, generate the logical address. What is the logical address? Of how much? 32 bit is there, right? 32 bit. So naturally it is divided into two parts, right? Two parts. What two parts? Page number, offset. For this 12 bits required, for this 20 bits required, right? 20 bits, right? This way, right? This 20 bits on this is the page table. Now this page table you have to work out on paging. So for dividing this page table, I have taken the page size of how much? 1 KB. Now see, if I divide with 1 KB page table, what happens? This further division will be there like this. You understand now? So let me take P1 and D1. Now 1 KB and miss how many bits? 10 bits for this, right? For this also 10 bits. Understand now? So now we have second level page table. So now see, 10 bits nothing but it is pointing to one page table like this, like you understand. This is a page table, is the page table is there, right? 10 bits nothing but how many entries will be there? How many entries will be there? So 2 power 10, 1024, right? 0, 1, 2, 3 like this, 1023 entries will be there. What this entry is containing? Some address is containing, address, X address. X address if you go, you will get one more level of page table, Here how many entries will be there here? So depends on this small d like this. In this case, we have a frame number. Take this frame number F value, pad it to original D. What is original D? This D. So this D you have to pad it. This will give the page or physical address. With the help of physical address, you can access the physical address space. I hope you understand now. I hope you understand this point. Fine. Now, sir, so here 1024 entries nothing but 1024 internal page tables possible. This we call inner page table. Inner page table we will call. This we call outer page table. Outer page table we will call. Or first level page table also we can call. Outer page table having the addresses of the all inner page tables. Inner page tables having the frame number of a physical address, physical memory. Sir, where inner page tables are kept? These all inner page tables are kept in secondary memory. That's why we can able to reduce the size of the page table. See, if all inner page table multiply with this value, you will get the same 2 power 20 only. Yes or no? If you keep all page table in main memory, there is no meaning how there is going to reduce the overhead, right? So now how many entries are there? 1024. 1024 inner page tables possible. This all 1024 inner page tables are kept in secondary memory. The moment it is required to access, particular page table is taken and put into main memory, access the frame number, then given to the process. So this will increase the time. So because one M required for outer page table, another M is required for finding the inner page table, another M is required for accessing the physical address space. Time will increase, but space is a concern for me. Space is a concern for me, so that the space will reduce. What is the space? Page table overhead will reduce here. Page table overhead it will reduce now. I hope you understand my point, all of you. So this way we do the multi-level paging. Fine. So chalo, one question we'll see. This is a question, right? Here is a question because it went front side. Look this. Consider a system with 16 GB. Consider a system with 16 GB logical address space and the number of frames already given in a physical address space is what? 64K frames are there. And what must be the page table size in this system such that page table of a process must fit in one frame of a physical memory. Assume that The page size is power of 2. Page size is not given, they are asking to find out the page size only. And important information given that, so theoretical I mentioned, page tables we need to keep into main memory only. You said what must be the page size, so that such that page table of a process should fit into one page only. So means with this data I can write page size should be equal to page table size. Page table size. Continue. How to get the page table size? We know number of entries, if I take capital N into E is a byte, right? This is the size of the page table. We need to get the page size, you have to compare, you will get the value. So this is given information now. This is given. See, they said you want to keep the page table in main memory only, but that has to fit exactly the one page size. One frame is one page size only. So how to get this information? First of all, try to get the page table size. So now see page table. Let page size. We don't know page size. Let take 2 power of k. Let take 2 power of p. 2 power of p bytes is the page size. Getting my point? Okay, now. So what is needed? Page table. Page table size you need to find out. Page table size you need to find out, right? How to get capital N into E bytes, right? What is the capital N? Number of pages in virtual address space. Number of pages in virtual address space. Look, see. So I am finding number of pages. Pages, that is capital N, where in logical address space. How to get, sir? Total logical address space divided by page size. You have to do it, right? What is the logical address space? Are they given in the question? The system is with 16 GB logical address space. They said 16 GB they given. Divided by page size how much? We don't know, right? 2 power of p bytes. So this is, can I express 2 power of 34? 34 bytes by 2 power of p bytes. So this gives 2 power of 34 minus p bytes. Am I right or wrong? So byte cancel, right? Is it correct or not? 1 GB 2 power of 30, 16 2 power of 4, 34. 2 power 34 minus p will be there. And we need to find out the E. What is E, sir? What E essentially contains? Are they given in a question E? Not given, right? Essentially contains a frame number bits. Please understand, frame number bits, some other information also will be there. Other information which you studied, like will be there, like protection bit, valid, invalid bit, this will be there. So F value you have to find out. How F value we have to find? F meaning what? In this case I have taken F, F nothing but frame number bits I want. Frame number bits depends on this F bits if I write it. Frame number bits depends on the number of frames in main memory. M if I take as a number of frames, M. So that you can write log of capital M base 2. M is what? Number of frames. Are they given in the question number of frames or any information is there? They said here number of frames in a physical address space, they get 64K. Substitute here log of 64, can I write 2 power of 64K, nothing but 2 power 16 base 2 can I write? So this gives the 16 bit. So now E we got, right? Yes. So I can substitute here. I can substitute page table size. Size equal to N value how much? 2 power of 34 minus P into E. What is E? E how much you got? So other information you can ignore because not given anything. We can ignore. F only I will take 16 bits. 16 bit means can I express as a 2 bytes? 2 bytes. So this value is 2 power of 35. 35 only. 2 power of 35. So 35 minus P, right? 2 power of 1 only, right? Let's take suppose this may not give, let's do it like byte will be there, right? Byte will be there. Okay, now see Understand, all of you. Understand now. Understand. So page table size equal to page size only, right? Page size only. Page size only. Now understand 2 power of 35. So 34 is correct only, right? 16 GB 2 power of 4, 34. 34 minus P only. Fine. That's 16 we got. Okay. Let's have 34. This is P. This is byte equal to page size. You assume P bytes we assume, right? Byte cancel. So we can equate 35 minus P equal to P. So 2P equal to 35, right? P equal to 35 by 2. So what I can do, like to get the values, what we can do, let me take it as a frame bits. So frame numbers, how many are there? 64, like 64K is there, right? So frame number, let's take, suppose if I modify, it is like giving, let's take 128K are there, assume that 128K. What happens here? Let's see, 128K. How 128K nothing but 17 bits, right? 17 bits. This gives the 17 bits, right? But right, E value. Okay, E value 17 bits. But E generally we express in terms of bytes. So 17 bits when you start expressing, you have to express as a 3 bytes. 3 bytes. 3 bytes only. Will it give 3 bytes here? 3 means we cannot express it, right? Let's take, okay, TK, this is only same only. Okay. So now what happens now? P equal to 35 by 2. 35 by 2, nothing but what? So this is 16, 17, right? 17 point something, right? This is nothing but I can take round of 18 bits here. Because actually some value equality should taken. Then I can write it, approximately page size will be, page size would be 2 power of P. Here is byte. 2 power of P almost 18. 18 nothing but watch. So 256 kilobytes is the page size. 256 kilobytes page size. That will fit same. What you can take it like, it is suppose if it round up to 34, it round up to 36 makes sense here because half is there, half we cannot consider it. Then what we can do for that, this address space need to be increased little more. Then things will work out. Suppose example, if I take physical logical address space, if I taken as a, instead of 16 to 32 bit, if I taken 35 will be get. So what we can do, so this we can change it like this. So this will change 32 GB, will take it 32 GB. 32 GB means what happens here? This is going to be 32 means 35 will be there. So this is going to be 35. Let me modify 35, right? 35 by P. So 35 minus P will be there. Then the remaining keep it 16 only. Remaining keep it 16 only. 16 only. Okay, next. So this is 35 minus, right? It will give 36. So 2 bytes only, right? 36. So 36 minus P. This is 36 minus P. What happened? 2P equal to 36. 36 nothing but how much value will be there? 18 only. 18 only. 18 is 256. Yes. So that value you can change it. Because ultimately understand what is the agenda of question here. You want to fit the page table into one frame. They are asking that size of the frame. So we have to do the comparison. This line is important. This line is very important. Like page size equal to page table size, you have to take it. So this we can solve it. Look at the another question. Look at the another question. Consider system with a 46-bit physical address and page size is 8 KB. The system uses multi-level paging. It is using multi-level paging. The page table entry size 4 byte. What is the number of entries in a last level page table such that the last level page table will fit into one page only? They are asking number of entries. It is similar question only, but he did not ask here how page size. They are asking that how many entries would be there here. Page size is given already. And entries asking, and that page table is fitting into one page only. Let's work out more. Let's work out here. So what I can do here? So this process who is running in a CPU like this, generate the logical address. How much? 46 bits. Sorry. 46 bits, right? 46 bits. Then you have to do the paging. One level, first level paging, you will do it. Page number and offset. What is the page size they given? 8 KB. So 13 bits are allocated here. Remaining all be 33 bits will be there. So now I am writing first level first level page table. Page table. How many entries would be there? 33. 2 power 33 entries will be there or not? Yes or no? This many entries will be there. If I multiply with the entry value, what is the entry value they given? 4 byte. What this will give? First level page table size it will give or not? Tell me, first level page table size will give or not? So this value how much? 2 power of 35. 35 only? 35. Yes, 35 bytes will be there now. Then you have to do further. They did not give a how many levels you have to do it. But if you go level by level, first level, second level, third level, multi-level paging if you do, last level will be fitting into one frame. That's what he is asking, right? Let's go with second level. Suppose second level page table size. How to obtain the second level page table? Then 2 power of this how much value? 35. 2 power of 35 is a page table, right? Divided by page size. What is page size? Page size how much? Page size is 8 KB. 8 KB. This gives how much? 13 you remove. 2 power of 22 entries will be there, right? You have to multiply by the entry size. How much? 4 byte. So this can I express 2 power of 24 bytes. This is second level page table. Then third level, level page table size equal to this size 2 power of 24 bytes divided by 8 KB. How much this give? 13 you removed. 2 power 11 entries will be there, right? This many entries will be there. This is only. Fine. What is the page size given? 8 KB given. Now he said. Further can I go? Suppose if I multiply this one into, what is the, if I multiply into 4 bytes, what is the value it is giving? 2 power of 13, 2 power 13 bytes. 2 power 13 bytes nothing but 8 KB or not. Now understand, outer level page table size 8 KB or not. He said now, last level page table size will fit into one frame on. What is the frame size? 8 KB. Can I do further division? So 2 power 13 by 8 KB if you divide you will get 1. That's not, you should not go to fourth level, third level enough. In the third level only, this third level page table size we got, right? Number of entries multiplied by entry size, third level page table size we got. That is equal to page size or not? Page size given 8 KB. So you have to stop third level only. We got the answer. Now what is the answer? It's not 8 KB answer. They ask how many entries are there? Entries you look, this is entries. How many entries are there? 2 power of 11. So 2 power 11 nothing but 2048 is the answer. 2048 is the answer. They asked what is the number of entries in a last level page table such that last level page table will fit into one page. So one page is fitting already. So 2048 is answer for this question. I hope you understand. Like this you can do it, Fine. So this is the simple paging concept. What simple paging I said mention? In a simple paging case. So there are performance if you see spatial and temporal. Temporal things can be solved by having TLB. And spatial can be solved like to reduce the page table overhead by using the optimal pages, and second was a multi-level paging, right? So now what is internal fragmentation suffering or not? Page table will suffer from the internal fragmentation. Page table, please understand. So paging, I'm writing paging, paging suffers from internal fragmentation, right? To solve this one, we are using segmentation. We are using what? Segmentation. Please understand segmentation. So this segmentation, internal fragmentation won't be there, but another problem will come. So what is the external fragmentation? Yes, this only for format. Segmentation, what we do? Unequal sized page. So in a paging, entire program divided into same sizes. And segmentation we don't do same size. We will choose unequal sizes. We segment will do distributed over the memory. Like a page table, we have a segment table to translate logical to physical address. Performance same. Temporal issues can be solved by having the TLB. Spatial issues, what can be done? Again, we have to do paging on a page table. Paging on a segmentation, we can do it. Paging on a segment table, if you do it, those page table you can put a secondary memory. So that can minimize the page table, segment table overhead. Getting my point? So this observation you can do it. Segmentation will not suffer from the internal fragmentation, it suffers from the external fragmentation. Now over all the mechanisms you observe, either internal external suffering or not. Fixed partition suffers with the fixed partition suffers the internal fragmentation, that we resolve with by using variable partition. variable partition suffer with the external fragmentation, that is solved with the paging. Paging again suffer with the internal fragmentation, that we solve with segmentation. Again segmentation started suffering with external fragmentation. We can minimize it, we cannot avoid it. So practically we can go with a segmented paging concept to reduce the further things. These are the concepts. Now next topic is virtual memory. So what is the virtual memory saying that? All of you please understand. Virtual memory. All of you, yes. What are the things need to understand? Virtual memory definitions already you know. Means there are two reasons to occur the virtual memory. Virtual memory is not a memory, please, all of you please make note of it. Virtual memory is not a physically existed. Virtual memory is a concept. It's not a memory, it is a concept. Existed memories are main memory, secondary memories only. Virtual memory concept means there are two reasons for using the virtual memory. If you look at the program, first reason, some part of the program may not be going to be executed at all. Do you know? Suppose some portions, if you see, some portion of program never get a chance for execution. Example, else parts are there. Else parts never get. And second thing, entire program is not required to, entire program is not going to be executed at the same time. Suppose 10 KB program is there, 10 KB program will not going to be executed at all. Then thought came like, what is the need of keeping entire program into main memory? Main memory is what? Limited memory, limited memory. So what is the need of loading entire program into memory? Don't load. Required thing only load, remaining you put in secondary memory. That's what concept of virtual memory. So that what happens, sir? If you not keep entire program main memory, many programs you can create. That means throughput will increase, CPU utilization will increase. That is the advantage. Now what is the disadvantage, sir? If you keep these pages in secondary memory, then total time execution will increase, right? Yes, we increase. Then hardware side DMA controller, we can put it to transfer these pages in a bulk rate into main memory to reduce these times. That we can do it. We can optimize this, what access time from secondary memories. So majorly main memory will reduce. Getting my point, all of you? This concept virtual memory. So virtual memory performance, we have effective memory access time. Effective memory access time. See, here this implemented, this virtual memory implemented by paging one that we call demand paging. That we call demand paging. Please understand. Demand paging. All of you know, right? Demand paging. What is demand paging says that? Pages of a process loaded into main memory based on the requirement, based on the demand only. So this demand paging can also be two types. One is a pure demand paging, demand paging. Some second was a prefetched demand paging. Getting my point? One is pure and second was a prefetched. Pure nothing but don't load any page of a process, everything you keep in secondary memory. Then start execute with empty things only. If you start executing everything, what happens? First reference is going to be miss or not? That we call a page fault. Yes, it can be missed. Whenever page miss occur, that page, required page you have to get from secondary memory, place into main memory. You have to do this service actually. The event page fault occur, we have to service that we call page fault service time. We call page fault service time. That's what you see, like effective memory access time of a demand paging. If you observe demand paging, okay, look this. If I take P is a page fault, if there is no page fault, one memory access time required. If page fault occur, I have to service, we call calling as S. This important equation you might have noticed here, where S is the S is a page fault service time. The event when page fault is occur, the required page need to be bring from secondary memory to main memory. So during, like when you bought it, if main memory is full, again you have to apply some replacement algorithm, remove one of them, place it, lot of activity you have to do which you know. So that all will take the time, that is S. When there is a page fault, S is required. No page fault, only M is required. This expression for performance of virtual memory that is implemented by demand paging now. Fine. So I hope you understand this point, all of you. I hope you understand all of you this, right? So noted, right? So this expression is like in 2000 recent 20 paper, there was a question also like this. They asked question based on this expression. Fine. So as I mentioned, all of you, Under demand paging only page replacement will occur. How, sir? The moment page fault occur, the page we need to fetch from secondary memory. I bought it, I want to place it in main memory, but memory is full already. Then what to do? One of the frame from main memory, one page we need to be remove. If the removal page is dirty, modified, you have to write back. If removal page is not dirty, not modified, you remove, place it. So which page you have to choose for replacement depends on the page replacement algorithm. Depends on the what? Page replacement algorithms. Page replacement algorithms, all of you. You study this page replacement algorithm. Various page replacement algorithms are there. FIFO, first in, first out. Second one is optimal algorithm. Optimal algorithm. Third one, LRU, least recently used. Fourth one is MRU, most recently used. And fifth one, you know, counting, least frequently count. And sixth one, most frequently count, like this. Second chance algorithm, like there are many replacement algorithm. What is the purpose of this replacement algorithm? To minimize the number of page faults, please understand. And this is very important also on this topic, because we can expect the question. Many times I have seen these questions are asked based on FIFO, optimal, LRU, MR, they asked. Yes, they given some reference string, they given number of frames, they ask simply how many page faults occur with this given reference string. What is the page iterate, like it ratio, miss ratio, like this kind of questions we can expect from this area. Please go to, these are easy topic, these are the easy topics only, fine. So reason you understand, occurrence of the page replacement algorithm, when there is a memory is full and to place a requested page, then one of the page choose and based on the algorithm and removed and place the requested page and update the page table value. Ultimate agenda of page replacement algorithm to minimize the number of page faults. I hope you got the point, right? So these are the things you would study from the memory management. So various mechanisms I mentioned, and little time I'll spend to understand. What are the important topics. Please understand what are the important topics we have from file system which we need to study. From file system is concerned, all of you. From file system is concerned, look all of you, file system is concerned. So first you'll please understand all of you, directory structures, structure you need to study. So directory structure we call, you know, file allocation table. Okay, in case of Windows operating system, we call directory structure. So versus inode structure will be inode structure. So inode structure in case of Unix or Linux operating system, inode structure. This also we can get the question from inode. Then followed by file allocation methods. File allocation methods. This is important thing. Then third one is what? Disk scheduling algorithms. Disk scheduling algorithm. This is important thing. These are the major important points one can see. When it is considered high node structure, easy question because how the question is framed, please understand. If you look at the structure of the inode, then majorly two things will be there. One is general attributes will be general attributes. This is the location attributes we call it. This is general attributes. This is the location attributes. General attributes, what will be the type of the file, like ownership will be there, ownership size will be there, that all the things will be there, fine. When it comes to location attributes, this based on location attributes only question we can get it. So there would be some 10 direct, please understand, direct addresses will be there, here, addresses is one single indirect addresses, and second one double indirect addresses, address block, then one triple indirect addresses. What does mean, sir, this all? So under this mechanism, please understand, see what we do, whenever a process comes, file comes, some blocks, data blocks need to be allocated. For request data file, data blocks need to be allocated. Here 10 direct data blocks will be there. Getting my point? How many 10 direct data block will be there? Let's take data block size is 1 KB. So now 10 KB data will be there. Any file size whose less than or equal to 10 KB, this data block can be assigned. If any file is required more than 10 KB, we have chosen one single indirect block. Then double indirect, then triple indirect goes like this. Then the question, possible question they can ask here. There are two type of question they can get. One question is that, what is the maximum file size possible with respect to disks? This they will ask it. Second question, what is the maximum file size possible with respect to inode structure? They will ask inode structure. How sir? Look, say, let I am taking let disk is, let the disk contain the two things. One is disk block address will be there. Disk block address will be there. Address means entire disk is partitioned into blocks. So each block is associated with the address. Then disk block size will be there. Let's take 1 KB. 1 KB. Fine. So disk size, how to take the disk size? The disk size will be how many such blocks possible? Nothing but 2 power of disk block address multiply by disk block size. So this is 2 power of 16 into 1 KB. That nothing but how much? 64 MB. Now see, maximum disk size how much? 64 MB like this. Now understand, if I ask question, what is the maximum file you can store with respect to disk? Nothing but 64 MB only. But question they will ask. So with respect to this file system, what a maximum file size you can store it? Sir, what happens here? Here a disk block 1 KB, right? As I mentioned here, there are 10 direct pointers will be, I am placing address of the disk block, 10 will be there, 10 I will point it, 10 data block I will point it. Here is one single indirect, nothing but one data block will be there here. This data block contains addresses, please understand. This data block contains addresses of the data block here. This is also data block which is not contain the data, which contain the addresses of the next two data blocks like this. These all are data blocks. Sir, now you understand this kind of index, is indexes of this one. What is size of this data block, this block, sir? So now we have to get it like this. Suppose, see, so disk block address how much? One disk block address 16 bit, right? Now see, 16 bit. Number of entries in one block, disk block. How to get disk block size 1 KB divided by entry value 2 byte. So now that is meaning 512 entries will get it. So, sir, what does mean, sir? So look this, what I am trying to say, all of you, what I am trying to say. Here is, so 16, so now disk block, this was 16 bit I stored here, 16 bit I stored. Here is one data block which containing the addresses of the next two data blocks. How many addresses you can keep it? That depends on the address length. That's what I say. Address of the one data block 16 bit. If I divide by the total blocks, you will get this many entries, means this many data blocks address you can keep it, like I am writing. So 0, 1, 2, 3, 4, 5, 11. 5, 11 entries will be there. Each entry 16 bit data, 16 bit address will be there, which is pointing to data block like this. One level. So now how much size will be there here? 512 into 1 KB, right? So now 512 KB can store. Now see, one single indirect if I use, maximum file size you can occupy here 512 KB like this. Now whatever one double indirection, now double indirection means there is a data block which contain the addresses like this. How many addresses? Possible 0 to 511, right? Last one. And each having the address of another. This also data we are not, this also address 0 to 511. Getting my point? Now this is pointing to the data block. This is pointing the data block. Getting my point, all of you? Now these are the data blocks only. Getting? 2 level will be there. Here 3 level will be there. So let me write it here. Let me write it now. Suppose one single indirect equal to what happened? 512 entries will be there, 1 KB. So 512 KB file size possible here. If I take, so second one, one double indirection. Double indirection. What happens? First data block of 512 entries. Each 512 entry pointing to next 512 data block which contain the address again 512 into 512. Then it is pointing to 1 KB of data. I hope you understand this one. So 2 power 9, 2 power 9, 2 power 29, right? 2 power 29, 512 MB file is possible like this. If I take one triple indirection means 512 into 512 into 512, right? Into 1 KB. This gives how much? 2 power 9, 2 power 9, 2 power 9. How much? So 18 plus and 27. 27, this is 37, right? 128 GB. Am I right or not? Now see, putting together, what is the maximum file size? Maximum file size possible with respect to inode structure is 128.512 MB. 512 MB only? 512 MB approximately. So not MB, you have to express in terms of 512 GB, you have to express it. All of you, I hope you understand this point. All of you. Yeah. So this type of question many times I have seen in paper. This type of question we have seen in many in paper. Next. So file allocation methods. File allocation methods, there are three types. Three we have. One is contiguous allocation. What does mean file allocation? Simply, when file comes, what are the data blocks you have to give it? Continuous data blocks need to allocate it. Second one, non-contiguous. Not contiguous. Third one is indexed allocation. So non-contiguous also known to be linked allocation. Linked allocation. See, either what are the things we need to observe here? One is internal fragmentation point, one is external fragmentation point, then access type, and one more thing you have to notice, like increasing the file size possible or not. Contiguous allocation means whenever any file comes having of a 6 KB also, data block size 1 KB, 6 data blocks. From anywhere you start, continuous 6 data blocks you need to allocate it. So there will be internal fragmentation as well as external fragmentation also, please understand. Internal as well as external only. Because what happens here, you can start anywhere, right? Somewhere middle blocks will be empty, that may not be utilized. The access type is satisfied, sequential and random, both can be satisfied because we can maintain the pointer. When it comes to contiguous, the non-contiguous linked allocation, internal fragmentation will be there. Linked allocation means what happens? One data block if assigned, data block contain the pointer to the next data block, that next pointer like this. So it is not required to allocate contiguous. Any block you can point it. So any block you are assigning, that address you have to place into previous data block only, right? So internal fragmentation anyway will be there, external fragmentation won't be there. This is only support sequential access. Here file increasing possible, here may not, it is inflexible. Increasing the files is inflexible, this is possible. Indexed allocation. What we do indexed allocation case? For each file, separate one index block will find out. Suppose example, one file comes of 12 KB, block size 1 KB, 12 blocks required, right? 12 data block need to assign. We are going to assign 13 data block, and one data block contains addresses of the remaining 12. Index, it maintains the index for each file. Each file there is an index. Anyway, internal fragmentation will be there, no external fragmentation. It is support both sequential, random, increasing file size possible. So these are the things you have to notice. Asked paper, which of the following file allocation methods not suffer from the external fragmentation? Which one is not suffering? Which are not suffering? Non-contiguous index. They given a statement, which are the statements are right. So these two are not suffering. So MSQ question can be framed here. Getting my point? Chalo, this is one important. Now when it comes to disk scheduling, Ah, so discourse scheduling, please understand. There are, we have a first to come, first to serve. Second one, shortest to seek time first. Third one, scan algorithm. The fourth one was look algorithm will be there, look. And the fifth one, C scan will be there. And the sixth one is C look will be there. C look will be there. This you have to go and practice this all the 6 algorithm. There is a high chance we can get the question from discourse scheduling algorithm also. Means what is the purpose of discourse scheduling, which we know, right? So in the beginning of the session we observed, in the system there would be separate queues for each device. So disk, so you have to fetch the pages from disk, right? There would be more than one process request for accessing the pages from the disk. There would be queue, disk queue is there. Now when the queue is contain many requests, what are orders we can service so that so total movements, head movements can be minimized, the seeks can be minimized. One way first come first serve, second way shortest to seek time first, and scanning start from one end, it will reach to other end, then will turn. Look saying that it won't go to other end, it will see the last request of the other end, it will change the turn, and the circulars can it will wrap around like this. So there is differentiation, you know. So work out the some samples, so then you will be able to answer it now. I hope you understand. So these are the essential thing you need to revise. Ultimately again repeating from process like introduction part. So focus on system calls. From process management, you need to focus on the like process concept, process state transition diagram, CPU scheduling algorithm, IPC synchronization mechanism very clearly with variations, and deadlock part. Deadlock also like preventions and like bankers algorithm. When it is comes to memory, allocation policies, getting my point, and paging segmentation, multi-level paging, and virtual memory with the TLB, with the demand paging environment, page replacement algorithm, these all the things need to be understand. From file system, majorly inode structure will be there, and file allocation method, disk scheduling algorithms are enough. And physical structure of the disk anyway you studied from the computer organization, but that also you need to work out now. So I hope this entire session useful to you. So like those who are not watched also, like later you can watch and understand. It is like ultimately this is a beneficial for the GATE 2023 aspirants. So thank you so much for like putting this much effort to continuously attending the session. Thank you so much all of you.